company. They provide us some resources to do this event and make our slides better. And regarding the Zone 24/7, like their headquarters is in United States, San Jose, California, and also a technical branch in Lanka. Then they have another branch in United Kingdom also. And they have they are doing a lot of services, software engineering products, big data analytics, data science, embedded systems, technological innovation, remote monitoring, IoT, robotics and automation, next gen warehousing and logistics, and so and so. They are doing a lot of services to several customer bases all around the world. And I want to thank Zone 24/7 again. And here is some description about myself. I'm Lanka Wickramatunge. I'm finally undergraduate University of Moratuwa in the Electronic and Telecommunication Engineering Department. And I have done my industrial training in Zone 24/7 company in Sri Lanka. And I am a chief operating officer and co-founder of Circuit Breakers Robotics. Okay, well, from the day one, we have done you like basic Arduino things, like how to code Arduino. Like we use Tinkercad platform, right? I think you can remember. If if one of you could not participate to the event, please go through our video recording so you can catch up. So from this webinar is from the Arduino to PCB, right? So when it comes to Arduino, like there is microcontrollers and digital pins, analog pins, and we are connected our buses and our buttons and our LCD display through to the Arduino, right? So we are doing those similar things, like we are connecting the microcontroller to our equipments through a PCB, right? So we are making permanent connection through a copper path. So you will learn how to build a PCB in this session. We will learn those things from the scratch. Yeah. So flow and learning outcomes. This is the session 1. So there is 2 parts. The first part is done by myself. The first part is containing designing basic PCB from scratch. We are developing the Medibox project. I think you can remember Medibox introduced in our last session, and I will be giving you some understanding about the different phases of PCB designing flow. And also when it comes to the second part, I will be doing my session from 9 to 12. I am planning to do 3-hour session. And after that, Kitmin Wickramasinghe will take over to a 1-hour session, and he will tell you about how to approach your own microcontroller PCB design. Like it will be very interesting session also. And there is a second session. It will be on next week. And here we will be, the summary of the session is we will be introducing you the best practices in PCB designing, and also we will be introducing you how to manufacture your own PCB. Like we will be giving you various method how to manufacture in your home, and as well as how to manufacture right. Can everyone see my screen?
Yes.
Yeah.
Sorry, I got a power cut. Containing the advanced. This is regarding the second session. I told you Kitminaya will take over the second session. It will on at 12 p.m. PCB. You can learn a lot from his session also. Yeah, and then I will be telling you what is PCB. PCB, I would like to ask a question. I don't know whether the chat is enabled or not.
The chat is enabled now.
Enabled, right? So I want everyone's answers. So what is PCB stand for? What does it mean by P, C, and B? It is an abbreviation, right? So can you guys mark the chat box? Printed circuit board. All right, all right. I'm getting a lot of answers. Okay, your answer is correct. PCB stand for P is printed, C is circuit, and B is board. Let me show you some examples of PCB.
I think Lanka is having some connectivity issues. Yeah, let's give him some time to connect back. So yeah, PCB stands for printed circuit boards, and these are some examples of printed circuit boards that are publicly available that you guys might have seen. And this is sort of one of the famous examples, an iPhone with lots of flexible PCB components and things, the Arduino, and this computer motherboards. And this is also a famous example called microcontrollers that we'll be covering in the session. Let's see if the uncle connected back. Yeah, I think Lanka might be having a power situation. I'll connect him as soon as he connects. So last week we presented you how to design a PCB on a breadboard, right? And you guys designed this particular PCB design, and maybe some of you have bought the components and try to design it on the breadboard. And this week we need to introduce you all to why it's important to go from breadboard to an actual PCB design, because you can't sort of create a device, a real world product using a breadboard design. You need to actually design it on PCB and then introduce it into an enclosure and provide battery power and things like that. And Medipro's design has actually been sort of introduced to go that kind of a workflow. And here you can see that there are 3 steps for approaching the PCB design, which is first, once you have your breadboard design, then you can go into what's called a dot board design. There, it's sort of a board with lots of holes in the directions, and you can create your circuit using horizontal and vertical connections. So the Lanka is back in it, connecting again. And the third one is the PCB design step, where you go from Vero board to PCB design. There's no horizontal or vertical connections here. You just straight away build your circuit using the EDA tools. Those are electronic design automation tools. Dilanka, are you? Hi, Dilanka, can you hear me? Hello, Dilanka. Dilanka, are you audible? Hello. He seems to be having a poor connection. It's okay. I'll keep going on with this set of slides. So if you consider like the 3 different variations, or like if you compare and contrast these 3 different things, there are few important things that you need to understand. So like if I go through some of them, Verobot, it's easy to connect the components together, and in the dot board and in the PCB, you need to use like soldering techniques, as well as in the PCB design, you need to add another design stage and manufacturing stage. When you consider like connectivity wise, breadboards have temporary connections, while dot boards have permanent connections. So there is a suggestion to move on to the second session of the workshop. So give me 1 minute. Hi everyone. So I think Dilanka might need some time to get his connection issue fixed, and he's having some power issues as well. So but he's here again.
Yeah.
Dilanka, are you okay?
Yeah. Shall I take over here?
Yes. Can you share the screen,
Yeah.
or shall I keep?
No, I will share my screen.
Okay.
Can you enable share my screen? Okay, thank you. Okay, sorry again for I had a power cut. Sorry for that. Okay. Kitmina, I think you are here, right?
Yeah, I started from here, Dilanka. Sorry about the technical difficulties.
Okay.
To the
I think you know about what is breadboard. Yeah. And you know what is breadboard and how it becomes a messy one, and then the solution is dot board. dot board is a dot board and Vero board, and Vero board here there are continuous connections, and you can see how the dot board look like if we are building a PCB. Like, it's kind of messy, but better than the breadboard one. So the final solution is PCB. Here PCB, there are specific connections from one component to one component. There are specific. So this is a comparison regarding the breadboard, dot board, and PCB. In the breadboard, it's easy to connect component together. Like, we can get a jump wire and connect here and there very easily. And when it comes to dot board, it needs to solder some components together. Like you saw in the previous picture also, we have to do some soldering part here. And when it comes to PCB, like, we have to do designing stage. Like, we have to design this PCB using a software, and as well as then we have to manufacture it. So, and another thing is, when it comes to dot boards, it's permanent connection, and PCB it's also permanent. And you can see the green color thing, we call it solder mask, so it will add another protection area. And again, the breadboard connection can be easily disconnected. You know, when we are using a jumper wire, it can be easily get disconnected. So we have to memorize all the connection. It is a very hard thing to do. And when it comes to soldering them, no, so it will not break easily. And top of copper parts, like I explained you earlier also, there is a green color thing we call solder mask, and it will add another protection. And when it comes to breadboard, it's harder to debug. Like, when, let's say, if you let's say you got an error in your LCD display, right? So you want to debug it. So when you are debugging, it's harder in breadboard, because like, you need to go through every connection. Like, the jump wires are not reliable, right? So if there are so many jump wires, like it kind of messy. So we can't find exactly what connection, like what is the ground, what is the power, and what is SCL, and what is SDA. We can't find those things, right? So it's hard to debug in breadboard. So when it comes to dot board, it's easier than the breadboard, but there is some issues also. And when PCB, like, it's very easy, because there is only like specific connections. Like and also there are some test points. Test points mean, let's say if your PCB has 5 volt and 5 volt, and you are placing a test point to check the 5 volt connection. Like, does the 5 volt come properly or not, like that of thing. And the next thing is, when it comes to breadboard, we don't need any manufacturing process, and also the disadvantage is we can't do large scale process manufacturing. Like, let's say you want to build 100 of PCBs, like 100 of circuits. So then the breadboard is not a suitable method. And when it comes to the dot board, let's say you have to build 100 of circuits. Like, it is possible, but we have to put more time on that, because we have to solder some wires and do some soldering things. Like, it will time consuming, right? And when it comes to PC, like it's very easy. Like, we have to design only one time, and we can print or manufacture it like as we want. Like, many count. If we want 1,000, if we want 10,000 or millions, whatever, we can manufacture. It's easy to going for a large scale manufacturing. Comes to breadboard, like it will cost high, right? When it comes to, like, we have to buy a breadboard first, and we have to buy jump wires then. So it will made some initial cost. And when it comes to dot board, like, it may not cost very high, and it is very cheaper than the breadboard price, right? And when it comes to PCB, the cost will depend on the manufacturing method. Like, you can manufacture the PCBs on your home, as well as you can manufacture the PCB from a foreign country or whatever manufacturing company. So if we are manufacturing in your home, the cost will be less, and if you are manufacturing from China or any other country, like it will be less, but the manufacturing cost be less, but the shipping cost be may high, right? And the last point, the board is larger in size. You saw that picture. Let's say this may be a very similar circuit. Like there are so many wires, and the size is bigger, and the dot board size is smaller than the breadboard, and PCB is very smaller in size, right? And here is the PCB design softwares. Um, we can categorize them into mainly two categories. One is paid softwares, one is open source softwares. Paid softwares, there are so many examples, like LTM is one of the most famous software among the world, in the world. And also there is OCAD and SolidWorks PCB. It's also powered by LTM, and also Proteus, and Circuit Studio is also a product by LTM Designer, and Autodesk Eagle and Mentor Graphics, CADStar, so and so. There are so many softwares, but they are paid, right? And there are open source softwares also. KiCad is one of the most famous open source software. And also there is ECEDA. It is a product of JLC PCB or LCSC company in China. And in our session, we are focusing on ECEDA. You can go to ECEDA by scanning this QR code, or easily type on Google eceda.com. I will suggest you to go to that website right now. I think link is also in the chat. You can go to the website. So I am suggesting you to use a laptop, because we are designing a PCB. It needs a laptop. Like if you are on your mobile phone, it won't work, right? So you have to make sure you are on a laptop. PC, like you can use both laptop and laptop. So you are watching these things through a Zoom. So you can see this thing on your laptop, or you can see in your mobile phone. No, whatever you do, like finally you have to use your laptop for designing your PCB. You can follow with me. Right? I think everyone is there. Can you send a chat? Uh, are you there? Done message. Can you type done if you already gone to ecda.com? Yes, done. Okay. I got several messages. Okay, but I think there is more to come.
I also got many messages.
Okay. Okay, let's proceed then. I think you are there. In the meantime, I will explain the LTM Design and ECDA comparison. LTM Designer is a paid software, I told you earlier, and the pricing is started from $7,000 per year. It's a really large cost, right? More than 10 lakhs in Sri Lankan rupees. But there are free tools available also. Like as a student, you can apply their student version. You can use at free cost. Like and when it comes to the ECDA, it's open source software. Like it's free. You can use in anywhere. Like you can use it any purpose. You don't want to pay, right? And the second point is LTM Designer is works on Windows operating system only, and I think they have not developed on Mac OS or Apple laptops. And also when it comes to ECDA, it's a web-based tool. You can use it anywhere in the world. Like if you have a laptop and if you have a browser, you can access ECDA, right? And also there is offline tool also available. You can download the ECDA software to your laptop, and you can do PCB designing also. And also in LTM, there are so many advanced features, right? It saves our time. Like if we want to design a PCB, it's make us easier by those advanced features, right? But when it comes to ECDA, there are no much advanced features, but it's a simple and user friendly, and like we don't need any prior knowledge to do that. I will explain in next point also. In LTM Designer, we need some knowledge regarding the PCB. Like if we want to like build a PCB, we need some basic knowledge if we are using LTM. Like I'm not going deep in much in LTM because we are focusing on ECDA. And when it comes to ECDA, like no one need no much prior knowledge regarding the PCB. You can simply like go to the ECDA and doing some design by looking here and there. They are supporting collaborative works. Like I think it's this feature is on paid version, and in ECDA it support for collaborative works. Like you can collaborative works means you can build a PCB with your friends. Like we can get together as a group and build our own PCB as a group, right? So that's collaborative. And also in the LTM designer they have version controlling also. You know version controlling. I think version controlling is some Git. You if you know about GitHub, like it's a more similar like thing, right? And also another feature is advanced 3D capabilities during PCB layout design. Like in LTM designer, they have offered like so many advanced 3D capabilities. Like we can visualize our PCBs in many ways. Like we can build our own PCB in a 3D way, like more realistic way. Like there are some advanced features. In ECD also we can obviously we can build our PCB in a 3D way. We will be building end of the day, right? And those are not much advanced features, but you can build a general 3D design here. And in the LTM, custom libraries can be developed with added functionalities. Like in the LTM, they are providing their libraries also, or we can design our custom libraries and add more functionalities on that. Like we add schematic on our future slides. And when it comes to ECDA, there are online libraries. Like we can import libraries very easily, not like LTM. And when it comes to LTM, we have to generate Gerber files and bill of material. BOM means bill of material to manufacture PCBs and components. Like let's say we want to manufacture PCBs, the manufacturers need Gerber format files, right? When we want to order components, we need a list of components that is called bill of material, right? And when it comes to ECDA, like we don't need to separately generate those Gerbers and bill of materials. Like we can directly order the PCB through their website, because ECDA is hosted by JLC PCB. It is one of the largest PCB manufacturing company in the world. It's established in China. So we can, if we are using ECDA, we can directly order those PCBs from China at a very cheap cost. When it comes to LTM, like they are providing a major update in every year. Like you can go through LTM website and you can go through YouTube and search LTM 2021, LTM 2022. Like you will get a video about what they are doing in this year, what they are doing in next year, and what they have done previous years also. And ECDA, when it comes to software, using anywhere in the world, using a browser and laptop, like it's very easy. Okay, I think you are there, right? On ecda.com. Okay, let me explain you how to design a PC. There are 4 steps, right? The step 1 is list down the requirement. Let's say you want to build the alarm clock, right? Alarm clock, and you want to list down the requirement. Like let's say you want to display a time and you want to set alarms, you want to set stopwatch kind of thing. So you have to list down first what should be my requirement in my design, in my product. Then you have to collect relevant information. So what are the relevant information? Like let's say the first point is list down the similar products and compare features. Let's say you are building an alarm clock. You can see what are the alarm clocks available. You go to the shop, or you can search through the internet similar products available, and you can compare their features with you, and you can add some features, and you can downgrade your features, and also, and then you have to list down your all the components, right? What are the components we need? We need a microcontroller. We need to get a power, so we have to build a power circuit, and so and so. We have to list down all the components that we needed in our project. Then we have to go through relevant data sheet. Let's say like we want to build a microcontroller. Let's say we want to drive a buzzer, like to, and we need a transistor to drive that. We have to see what is the maximum current that can bear the transistor. Like let's say the maximum current that can bear the transistor is, let's say, 1.5 ampere. So if we give 2 amperes to that transistor, it will burn, right? So that kind of thing. First, then you have to go through all the data sheet, like if you are using those components. So what is the maximum capabilities it has? What is the minimum capabilities it has? So what the components domain, like what can do, what is it domain, like I think you can get the idea, like from the transistor explanation. And then you can brainstorm your ideas with your teammates if you have team, or you can get advice from a person who knows these things better. And yeah, like if you are building a circuit and you have to confirm its reliability, it is like it is a good circuit or it's a bad circuit, like it has safety or not, like you have to verify those things, right? So then you have to build a PCB schematic and then layout. I will be explaining you in the future slides what is schematic and what is layout. Okay, so this is the PCB designing flow. First, we will be designing schematic. I will be explaining in future slide what is schematic. Schematic is basically a wiring diagram. Like we are explaining through the schematic. What we are explaining is the connection between components. Uh, let's say this is a capacitor. So this is another capacitor. So we are connected those capacitors. So this is some sort of a schematic, right? This is also a big thing. And then the layout, right? I will be explain more things about layout in future slides, but get a brief idea. Layout is basically a connection. And there is a connection, right? There's a copper path. So layout is designing those copper paths. This is a rough idea. You can get a brief idea in future slides. So layout is basically make those connection in realistic way. Like how do we connect those things? That's the basic idea regarding the layout. And then we have to generate gerbers. Gerber is something like the manufacturer wanted to print the PCB. Let's say like we don't want to separately design gerbers. We have to generate through our PCB, like schematics and layouts. Like let's say we give you a simple example. Let's say Word document. You type a Word document, and you can generate a PDF also through that Word document. So this is a similar kind of thing. You will design a PCB and schematic and layout. There are two main components, and after that you can convert it to gerbers. Gerbers is a thing that manufacturer want, the machine want. This kind of thing. I show some examples in previous slides, and here we go. This is Medibox introduction. I think in our very first session also you got the basic idea regarding the Medibox. So I don't you build those circuits in Tinkercad and you have done coding. I think you are at that level right now. Anyway, that previous knowledge is not required in my session. I will be basically designing the PCB, and we will be first designing the schematic. What is, let's say, like we are between components and we are routing them. This is layout, the routed thing, and finally we will be generate our PCB. This is the final outcome. This should be our final outcome, right? Okay. I think you are there in ecd.com. ecda.com. When you are going to the ecda.com, there is you have to create an account. I think my internet connection is slow. First, you have to create your own, or you can use a Google account to log. What happened? Okay. This is the interface of ECDA. You can log in your ECDA here. You can either continue with your Gmail, or you can enter your email and password here, and you can log in. I'll be joining, entering my email. I think you can do parallelly with me, right? Okay, I am logged in. I think you are there. You have two options. You can use to log your Gmail, or you can use your email and the password, not your Gmail password. You can use your own password here, and then click this button, ECDA design, and you will be directed to this kind of workspace, and you will be see some this kind of messages. You can skip those initial messages. Try to keep on with me. If you are unable to keep on with me, put a message on a chat. So hereafter we are doing some sort of practical thing, like you are building the PCB parallel with me, right? So you need to make sure you and sure parallelly listening to me or looking at my screen, whatever. Like, do parallel with me. Don't look at this and like, let me say, let's say don't think you can see these things and it will like make sure you can you will be make a pro in PCB. Like you have to do these things in your own, otherwise you will be not um, hello, you will be not like you can't build your own PCB, otherwise you are not doing these things. If you are just watching these things, it will not make you have to follow with me. Okay. Then I can show you some there are sample projects. You can click these things. Let's say this one. If I am clicking that, it will open the sample thing. This is the this project is called telecontrol, right? Here you can see this is the schematic. Schematic, I told you, like schematic is the connection between components. Okay, so this is their final outcome. This one, I think you have played some games, right, using this kind of thing. Okay, those examples you can go through. There are so many examples also. I will show you one thing. And this is the another example. This is the schematic. It's a very big one. And this is the layout, its final outcome. Okay. All right. So the first step is opening a project. Like you have to create a project. Go to the file option here, right? And go to the new and then project, right? File, new project. On the top of the window, there is file and there is new and project. And here you can type your project. I will be typing Medibox, okay, right? Medibox project. Okay. If you can add a description if you want. Embedded system. Okay. I created a project, and here it's automatically generated a schematic. First thing that you have to do is save this thing, right? You can either press control plus S to save, or you can here you can, in the file option there is save option also. You can control plus S, or you can click the save option also, right? I will press control plus S. It will pop up a message on bottom corner, saved successfully, right? When it saves, it will pop up another line with sheet 1. So we are on that sheet 1, right? You can see that sheet 1 through that drop down arrow. If you are clicking on that Medibox project on the left hand side, there is a drop down arrow. You can see sheet 1, and let's say give a name. We can right click on that sheet 1 and you can click modify. Right click on that and click modify and give it a name. I will give maybe box underscore. You can give any name, right? Your own name. I will give Medibox schematic and control save. Okay. And okay, I think you are there. And I will be explaining some features with you. Here there is wiring tool, right? This is, if you are going through them, like don't click this. If you are waiting on your mouse with its icon, it's pop up wire. The first icon is wire. If you are clicking that, like you can see this green color wire there, right? And you can escape to you can press ESC pin, escape button to escape from that option, right? And there is a bus we will not using that option. And And also there is net label. Let's see in our net label is some naming thing, and also there is a ground, and also net port. Net port we are using to connect. I will be explaining in future. And VCC, this is a power symbol. This is 5-volt power symbols, and not connection flags. Let's say in your microcontroller you are not using any pins. You can place a cross for the not using pins, right? And you can voltage probe voltage in your schematic, and so and so. And here in the drawing, there is document setting. The first button is document. If you are pressing that, you can see the settings of the displaying schematic. This is the kind of thing. This is the width height, and it's on landscape. If you are pressing a portrait, it will generate a portrait. Don't place it. Press escape to escape from that option. Right? Okay. Those are the very basic features. I'm not going to every feature right now. I will be doing all the features parallelly with you. So, in the first, as a first thing, you can upload a photo, like let's say this one. Let's say add a title. Right? Go to this text box and click on sheet 1. Delete that name. Add the title. This medi box and press enter. It will change its name, right? And this is a revision number 1.0, and this is a sheet number. You can add your. I will add my company, University of Morocco, and press enter. And date and drawn by, you can add your name. I will add my name, Lanka Lakna. And there is ECD logo. You don't want to keep it here. You can delete that logo. Easily press delete button, or you can right click and there is delete option also. And then you can add your own picture and on your own logo. Let's say this in this drawing tab, right? This drawing tab, there is option image. Right? There are so many options. I explained document settings, and there are some behavior tool and text tool and pen drawing tool, rectangle, clips, and set canvas. You can, by choosing that for your application, and you can easily press on the image icon and select image. Then you can put a image URL from the internet, or you can select an image file. You can click this. It will pop up your your computer's folders. So from that you can pick a logo, right? I will pick a circuit breakers logo and press OK. Will upload it. Select an image. The logo appeared. It's a bigger in size, and place it and press escape button. appears as a big icon. And here you can small. I think my internet connection is a bit unstable. Sorry for that. You can make by dragging this icon very small. Sorry about my internet connection. It's a bit laggy. Okay, I place a logo. Right? Okay. Now you are, I think you are at that place right now. Place your logo, your photo, or whatever you need here. You can place your company logo over there also. Okay. And then I will be telling you what is this means. This is the designing manager, and it will show you your projects. This is project. This is project, and it will show your project and the project documents under your project folder. And then there's designing manager. Now there is no any designing connections. If you are connecting things, it will fulfill folder, and then the library in ECD is this resistors ground VCC connection, and by clicking that, you will pop up another window. Like you can search the library through that. Like let's say you want a resistor, type a resistor and play enter, and it will appear all the resistors. Like let's say there is this kind of things in only one component in LCAC, and one is in JLC PCB assemble. Like assemble means you can get, like you can see this icon SMT over there. SMT means you can get solders those components through the JLC PCBs. Like if you want to send your PCBs to China, you can get solders also your component. Like if you are choosing those kind of component, let's say like there are so many components. I search only one. Like let's say there is user contributed tab. There are so many resistors that users are contributed. Like let's say we are also users, no? So we can contribute all into to use others. So like this is open source software, no? So we can let others use our sources also. So this is the simply explanation of the library tab. So we are not using that right now because I made my libraries to access to you. I will be let you the link. Okay. This is the simple explanation of searching a library. You can search a component name, whatever component you need. You can search through the internet. Like it will appear the LCAC is a component selling site in China. It's selling electronic components online, right? We can order components from here, and we can place those components on our PCB very easily. And there are so many options. We don't want right now. So what I have to do is um, I will be put another link, or you can easily type. I'll be go through my slides. Okay, here what we left. Okay, right. I will be explaining what is schematic right now. Mm, okay, I left. I will be take over here. So what is the schematic? A schematic is the visual representation of a circuit. Let's say I explained those things earlier also. You did this kind of building, this kind of wire diagram using TicketCAD, right? And also now we are doing a converting diagram to a graphical representation by block and connecting wires, those kind of. And schematic is a virtual representation of a circuit. As such, its purpose is to communicate a circuit to someone else. The purpose of a PCB schematic is communicate a circuit to someone else. Like you have to explain the connection to someone else. That is the purpose of schematic. So schematic is to communicate information very quickly, clearly, without a low chance of misleading. So we have to design our PCB schematic very quickly, not need to be quickly, but if someone going through our schematic, he have to understand it very quickly. That what means by quickly, and it should be very clear. Like everyone should understand what I have designed, and the other people can be low chance of misunderstanding this PCB, right? So the next thing is I will be explaining like what is PCB library. Uh, PCB library, we will be saying schematic libraries. The extension of that file is .schlib, schematic library. Sch means schematic, lib means library. This is the extension. The simple terms that we can use to express schematic libraries is symbol. Schematic library. This is also, you can see the picture. This is the schematic or symbol of a Atmega 328P chip, right? You can see the every pin put here, right? Okay. So schematic component symbol are created the schematic library. So this is the symbol. Like I told you, this thing we call symbol. This represented this microcontroller, right? And the next point, specific parametric information. Like this, if we are using schematic libraries, it specifies specific parametric information. Let's say I told you about bill of material. In the final stage, we like if we are building a PCB, we have to order those components from a manufacturer, component manufacturer. So to do that, we have to come up with a list of components. Like a bill of material is a list of components. To making the bill of material, we should have schematic libraries. The bill of material will generate from the schematic libraries or the symbols. Okay. So the schematic, there is a component name and what type of component. This is U1, this is U2, U3. We are representing U symbol to IC, integrated circuit, and this is the component name. So by those details, the bill of material will generate, right? And we can include some simulation files to the schematics also. This is mean by my last point. you can add your PCB simulation to your schematic. It is not a needed thing to do to right now. We are doing a simple PCB building. Okay. Okay. The next thing is PCB schematic features. There is visual and logical structure. What does mean by visual and logical structure? Let's say you have to design PCB schematic in order to like this is my schematic. Here you can see my high power things, the input power VCC or 5 volt in the upside, and the ground is on the downside. This is the convention. This is a convention, right? So here also the 5 volt is the upside, ground in downside. If you are putting the ground on the top and VCC on the bottom, it will not accept it. Like it should have some flow. And also we have to design our PCB schematic. Like let's say you have to place input components on the left side and output components on the right side. I put my power connector. Power connector means we have to input power. We have to plug our battery through a power connector. So this is the input. It should be on the left hand side. Let's say the LCD connector on the right side. It is our output. So we should have some sort of a flow, right? Input to output, left to right, and power up to down. High power is on the top side, low power is on the bottom side. Let's say if you have minus voltages, those are on lower than ground, right? So there should be a flow. This is meant by a logical flow. And also you have to place components that others can easily understand. Let's say you are placing a transistor this way. This also can understand, but if you are turning this transistor here and there, you can place it. If you are placing in another angle that we cannot easily see and understand it, it's not an acceptable thing. Like you have to place all these components in like very easy manner. Like let's say I put my transistor like that and put my buzzer like that. I think you all can understand like what is the PCB flow, logical flow. Like don't get much burden to that. Like I will be explaining through the designing also, and the multi-level hierarchy. Multi-level hierarchy means like let's say your PCB is very big thing. Like you can see there are, this is microcontroller circuit, power circuit, power connector, push button circuit, and buzzer circuit, so and so. So you don't want to build all the things in one circuit. Let's say it has so many other circuits and it will fill up, it will become a machine. So you can build separately those circuits in separate sheets and you can link those things. So this is called some sort of hierarchy. So it is meant by that point. And there is a electrical role checking. Electrical role checking means like let's say you have made the wrong connection. Let's say you directly connect 5 volt to ground, right? Let's say you by your mistakes you directly connect 5 volt to ground. It's a mistake, no? So the software will automatically check the electrical rules. So you have done these things in a good way or a bad way. This is the feature offered by schematic design. And also you can import and export. Let's say like you can import any component symbols, and also you can export a PCB of your schematic. It's what I did was I export my schematic design as a PNG. This is also exporting thing. So this feature is also offered by schematic design. And here we go. The first thing that we have to design is uh, microcontroller circuit. Okay, and you can go to my libraries by scanning this QR, or you can simply type this link. Like you can ecda.com/dilanka l/components. I think the link is on the chat right now. You can go to the link and I will be show what does it look like. If you are clicking that, it will be linking to this interface. This is my ECDA account I created prior to this project to make it easier. Actually I got this component by searching from the ECDA library. I showed you previously this one. I showed you how to search a library. I make all these libraries by searching, and I made all the assessments and make it available for your usage, right? So what you have to do is you have to simply go to this thing and press star mark, right? Press star mark for all these components. There is 4, 8, 12, 16 and 17 components. You have to press star. If you are pressing star, it will appear on your account under the favorite category. Right? I will show you how to place a star, right? This kind of star. You have to put a star. I will be show you my account. I already put a star. I think so many people put a stars. Uh, they are not equal. Please put all the components to a star. Like otherwise, it won't appear on your ECD account, right? You will be making a trouble. Please put star to all the components. Make sure to put star on all your components and put a message if you have completed that one. If you are up to that, put a message on your chat. I think 65 people there. How about others? Okay, I'm getting a lot of messages. You are so many. There are so many enthusiastic persons. Okay, I'll be refresh. Oh, there is 91. Okay, good. How about others? I made all these stuff, right? In my account, I import. I am in a different account. This is my new project account. I am also done the importing things from this stuff, making stuff. Right? Okay. 95 people are there. Okay. Now you can see, you can go to your ECDA and then you can go to your library tab. Under the library tab, you can click workspace. Right? If you are clicking workspace, the workspace, it appears my library and my favorite. Nothing appears. But if you are clicking my favorite and if you are clicking all button here, and it will appear all the libraries. Like you place a heart. Heart means you are adding to your favorite, right? You are adding my libraries to your favorite list. Okay. I think all of the people there. Let me check. Oh, 100 pass. Very good. I want to give you a reminder. I will be telling in Sinhala also. Like, ඔයාලා කියන්නේ මේක බලන් හිටියට අර පුළුවන් වෙන්නේ නැහැ. මේක try කරලා බලන්න ඕනේ පුළුවන් වෙන්නේ. මේක ඇන්දොත් තමයි ඔයගලන්ට මේක පුළුවන් වෙන්නේ. නැත්තම් ඔයගලන්ට මේක පුළුවන් වෙන්නේ නැහැ. හරිද? කියන්නේ මාත් එක්කම parallelly මේක design කරන්න. ස්ක්‍රීන් එක දිහා බලන් හිටියට ඔයාලා හිතන් හිටියට මේක පුළුවන් වෙනවා කියලා එහෙම පුළුවන් වෙන්නේ නැහැ. මේක කරලා experience එක ගත්තාම තමයි ඒ confident එක එන්නේ. Again, try to keep on with me, right? You have to build your own. Okay, I think we can proceed. We have more than 100 participants on board. Okay, I will be going to my presentation again. Okay. All right. So we are building a first circuit right now. I will be explaining what are the components. We are building microcontroller circuit here. There are three major parts. First one is oscillator circuit. Second one is reset button circuit. Third one is LED circuit. So when it comes to oscillator, there are three major components. One is this one, right? Atmega 328P PU chip. And you have to place a crystal oscillator. This thing is oscillator. Xtel one, 16 megahertz oscillator. Right? Like it will work as a clock. I'm not going to much deeper in electronic areas right now because the purpose is focusing on the PCB design, right? And we are using 22 picofarad capacitors. You can see the physical pictures also. This is the Atmega 328P PU chip. This is also in Arduino Uno board. If you have Arduino Uno, this is the chip Arduino Uno has, right? We are building some sort of Arduino Uno by ourselves, right? Okay. Uh, I think you understand. This is a oscillator look like this, right? Right. Okay. Then we have 22 picofarad capacitors. It appears like පරිප්පටේ දාල් පරිප්පටයක් වගේ තමයි, right? Then the reset button circuit. Reset button circuit. We have a push button like that. I think you have seen that, and also resistor, a 10K resistor here, and 0.1 microfarad capacitor. 0.1 microfarad equals to 100 nanofarad. මේ දෙකම සමානයි. 0.1 microfarads කියන්නේ 100 nanofarad තමයි. Okay. Then we LED means this 330 ohm LED bulb. This is the 330 ohm resistor, and this is the LED bulb. I think you have seen in your life. And this is the 0.1 microfarad capacitor. Okay. I'll be going to my design game. So I'll be first placing my Atmega 328P microcontroller. Simply click on here and click on place button, and the schematic symbol will appear, right? You can place let's say here, okay, and press escape button to escape. Otherwise it will place so many items. Let's say you in a mistake you place two components there, like you have two components, right? You don't want two ICs, so simply click on one thing and press delete button and it will disappear, right? Okay. And you have microcontroller right now, and then we have to build our oscillator circuit first, and then again go to the library, press crystal oscillator. You can see crystal oscillator. If you cannot see any components, please go to that my library and make sure you have click the star button to make it appears as your favorite one, right? And place crystal oscillator, and you have this arrangement. But let's say you place in this arrangement, like it's harder to route. Let's say I put it in this way. If I put in this way, I have to route these two pins to pin number 9 and 10. And let's say I am taking wire, right? From here wiring tools, I am taking a wire and click on this edge and click on this edge and it wired, and click on this edge and go here and click here to stop here, and then again click here to connect. Okay, then if you are looking into that, this looks ugly, right? So this is not a nice thing to do. You can delete this wire thing and click on this component, and you can press space bar. If you are pressing space bar, it will like rotating, right? So you can escape bar and make sure you have this kind of arrangement. Okay, I think you are there. And also you have to place 22 picofarad capacitors. Okay, place button and place one here and other one here. Okay, press escape button, right? And it will appear as first capacitor as C1, second C2. So this thing as a designator. Designator is a component category. This is a capacitor. C means capacitor. I told you U means integrated circuit, IC. This is IC, no? And this is a crystal oscillator. Its designator is external. Okay. All right. I think you are there. And then you can place a ground. I think I told you place ground on the bottom side, right? Okay. Press escape button and go to the wiring tools and press on wire, and you will appear a wire. Okay. This kind of thing appear. And then you have to press on 9, and then you will appear wire. It's better to like don't go through this area, like it will looks ugly, no? You can stop here, like you can simply click here and go to upward direction, and again simply click here and connect to this, and again press 10, click here, click here, click here, and click here to click here to connect, click here to click here, connect, click here, and it should be connected to ground, and this also connected to ground. Okay, we are done with crystal oscillator circuit. This thing looks similar to this, right? Okay, I think you are there with me. Please put a message on chat if you are with me, because I want to catch up with you, because I want to design with you. I want you to learn these things. Please put a message on a chat to continue. This is the first thing. I know you make some time. If you need any time, put a message. If someone needs any time, put a message. Put a lot of messages like they have done. If anyone not done yet, please put a message. I need time. Okay. I need more time. Okay. So I need time. Okay. I'll be giving you another 1 to 2 minutes, and I will be explaining if you have any struggle. You have to go to library and pick a component. We first placed the Arduino chip at Mega 328P. You can select that, and you can simply click the place button, and it will appear like this. And I already placed, and I will be pressing escape button. If mistakenly you put a 2 design, click on one and press a delete button, it will disappear, right? Okay. Right. Do you need more time? Okay, done. Okay, I think you are there. Okay, we'll be next. Like I will be explaining simple things like clock keys. Like the we have, like say you are doing Arduino. Like you are coding, right? You are coding different. Like the first thing you say on the LCD screen, and the next line you will tell to Arduino display this, and the next line you will tell erase this, and next line you will tell and display this, and so you are coding this kind of way. So uh, so crystal oscillators responsibility is executing those instructions at a time. Like this is 16 megahertz, no? So it has like mega means 10 to the power 6, right? So it has so many capabilities. Like it can execute 6 to the power 10 to the power 6 instruction at a second, right? This kind of capability it has. The responsibility of this circuit is to executing your instruction. Can සිංහලෙන් කියනවා නම් අපි කෝඩ් කරද්දි line by line කෝඩ් කරන්නේ. ඒ කෝඩ් එකේ line එකක් execute කරන එකේ වගකීම තියෙන්නේ මෙයාට. ඊට අනුව numbers දෙකක් එකතු කරනවා කියන්නේ. එතකොට එකතු කරන එක මේ වෙලාවට මෙයා එන්න මේ ඊට පස්සේ මේ දෙන්නම එකතු කරන්න එකතු කරලා මෙයාගෙන් ගුණ කරන්න step by step process එක වෙන එක ඒ process එක නිකන් time එකට වෙන එක පවත්වගෙන යන්නේ මේ circuit එක. oscillator එකෙන් වෙන්නේ ඒක. Okay. All right. I think you are there with me. Then we will be building the reset button circuit. We have to place a reset button, 10K resistor, and 100 nanofarad capacitor or a 0.1 microfarad capacitor. Okay. Let me go to my ECDA and go to my library, and you can see where the push button. You can see push button. If you don't see a push button, please go to my library and add these things library by clicking start, right? Okay. There are so many people following me. I am pressing a push button and place, and you can place here. All right. And we have to place 10K. Let's see where is 10K. There is no 10K, but there is resistor. Okay. You can place a resistor and then you can rename it. You can pick a resistor and turn it this way by pressing a space bar. It will turn like this, right? You can place here and it will appear as R1, right? Resistor. You can rename this resistor with 10 and K. Enter. And it will appear as this, right? And this push button also you can rename. This is the reset button. RST_DT reset button. In the Arduino also you see a reset button. No, you can see a reset button in Arduino. I can see if you have Arduino, you can see a reset button there. Like if your code get interrupted or what anything happen, you simply press reset button to start over again, right? And also we have to place 1.1 capacitor. I will pick a capacitor and place it here. Okay. You place the components with me, and I have to place 2 grounds. You can click the previous ground also. You can click on the previous ground, Control C to copy, and again Control B to paste. Okay. One is placed here, and again Control B. I copied now, and again Control B to paste. Okay. Okay. Now we can connect those things. Press on wire tool and connect this and connect to the capacitor and then connect to the button and connect to the resistor, and this thing also we can connect the push button. We can connect this thing and here, and we can place it ground. Okay. Okay, I made connection, and now like if you can't find this ground is there, right? Or ground is there, you can find anywhere. Like you can get a copy and paste, or you can place a ground there, and then you have to place a 5 volt here. For that I will take the VCC thing and I will place it here, and I will be renaming it as 5V and press enter. It will appear as 5 volt. And get a wire and connect it. Okay. Now I am done with my reset circuit. Okay, so, okay. What I have done was I place a push button, 10K resistor, and 100 nanofarad or 0.1 microfarad. I pick a 0.1 microfarad. Please pick this, right? It will appear as this kind of symbol. Let's say there is another thing. There is another resistor called 100 nanofarad. If we are placing that, you will this kind of symbol. We told this thing to polarize. We tell these things to non-polarize. Polarize means it has plus and minus. Let's say if you have seen any capacitor, I will show you through my slide. In this capacitor also, you can see one lead uh, uh, is higher length than other lead, right? We told these things to polarize. And let's say when it comes to me 22 picofarad capacitor, those two leads are equally length. We told them non-polarized. Let's say you can see here, these are non-polarized, these are polarized. If you are explaining in Sinhala, polarized කියන්නේ එයාගේ leads දෙකක් leads දෙකක් තියෙනවා capacity එකට. එකක් දිගයි එකක් කොටයි. දිග එකෙන් mean වෙන්නේ එයා plus, කොට එකෙන් mean වෙන්නේ එයා minus. ground එක වගේ. එතකොට මේකේ ගත්තොත් picofarad එක දකින්න නැත්නම් ඒ leads දෙකම සමානයි. ඒ සමානින්ද තමයි මෙයාගේ අර වගේ මේ දාන්නක් නැහැ. අර curve එකයි ඊට තියෙන symbol එක නැහැ. ඒක තමයි difference එක. මේක pick කරන්න එපා. මෙතෙන්ට ඕනි polarize. තමයි මට කියන්න. All right. Yeah, someone is asking why do we need to rename the 10K resistor? Because it need to appear on the bill of material, right? Otherwise, there are so many resistors we have. එකෙක් කනවා වැරදුනාම y එක අයින් කරන්න කොහොමද කියලා. ඔයා y එක උඩ ක්ලික් කරන්න. ක්ලික් කරාම y එක රතු පාට එනවා. ඊට පස්සේ delete කියන බටන් එක ඔබන්න. නැත්තම් y එක උඩ right click y එක click කරලා ඒක උඩ right click කරාම delete කියලා එනවා. You can try both ways. Make sure to connect these two pins in a push button, right? Please make sure to connect these things in a push button. Okay. කට්ටියන 5 volts කොහෙන්ද ගත්තේ කියලා. You can find 5 volts on the EE library tab. There is VCC. You can take a VCC and place it there and press the escape button and you can rename it, right? Okay. Otherwise, you can find VCC here also. There is 5 volt. If you are taking 5 volt, remove that plus 5 mark. So you can keep plus 5 mark anyway. Doesn't matter. But you have to like be constant. Like you have to place plus 5 in everywhere. Okay. Right. I will be going into next step because the time is also limited. I have to stop this in 12. I think I can do. Okay. If you are purchasing component, I want to highlight this IC connector. Please buy this IC connector. If you are purchasing component, like this is not a mandatory thing. If you are buying this, like if let's say in your mistake, this IC got burned, right? So you have to place a new IC on your PCB. This is our PCB. So you have to place a new IC on that. So if you are solder this IC it will make a permanent connection. So you have to desolder it. So let's say if you are using this kind of connector, you simply has to pull it and again push the new component on that. It's up to you to decide. Okay, I was there, and we have to build a LED circuit. I will be doing first things in very okay. We have to pick a resistor again, place, and you know in the Arduino also default LED comes with pin number 13. You uh, you can go through Arduino datasheets also. You can place a resistor here and press escape button, and then you can go and pick a LED and place it here. Okay. Someone is asking what is the difference between +5 and 5. +5, you have to name it anyway, any type of way. Like you can either tell not adding plus mark, you can tell plus also, like in a typing. But you have to like there are many +5s in our PCB, but so you have to place all same name in the whole PCB +5. So otherwise it won't connect each other. Okay. All right. And I place these things and I will place a ground. I get a copy of ground and we press E to paste and get a wire and connect. Okay. All right. I think you are with me. I want to like now I want to place 5V to VCC and AVCC by connecting 2 pins and connect it to 5V. Right? We'll be doing that part. You can get a 5V from here. You can get a copy, Control C to copy and Control V paste. You can paste it here, but you can see like by placing here, like it will like distracting. So I want to move these components away, right? I can select these place it near to a analog reference button. Okay. Press escape and place a ground. You can simply click on ground, Control C and Control V to connect pin number 8 and 22, and again Control V, place it here to connect and get a wire, connect here and connect here, and you can connect this and connect to the ground. Okay. I think we have done the major part in our PCB, microcontroller PCB. Someone is asking how to put a ohm sign. You can simply Google ohm symbol. And you get a symbol. You can get a copy, 330 ohm. You can press the ohm sign. Ohm is not a mandatory thing. You can press R also. 330 R or 330 ohm, whatever. Um, uh, okay, I think you are on that right now. See, I place my 5 volt on the upside and ground on the downside. Otherwise, I can do the ground on the upside and 5 volt on the downside also, but there should be a convention, right? And the reset button is also input. I have to place this circuit on this side, but I am placing those things on left side because it is an input, right? Okay. Someone is asking started components is not appeared in his list. Please go to library, and if you are pressing this other tabs, it won't appear. Make sure to click on this workspace tab, right? I think you are having that issue. Make sure to select ECDA and symbol and also workspace. You have to click on those three. In case you have made some mistake, you have to press these tabs. Then you will having my library and my favorite. In my favorite category, you have all, and then you will display all the components. I think here you can catch up. Please make sure to press those three tabs. Okay. Right. Let's see what are the other things we have to do. These things okay. We have to place these things okay. And it is on other slide. I think we are done with these components. We place those components. The person who asked the previous question tell me it's all this problem, right? Okay. Next, we have to place our connectors. We have to place USB ASP connector and FTDI connector. I'll be explaining what is USB ASP and we are building Arduino board, like, but in the Arduino, you can see there are some like small chips here and there. There is a chip to convert serial data to like in the laptop you will be having a USB cable in the Arduino. Like you if you are programming Arduino, let's say if you are programming Arduino, you're using a USB cable. Through the USB cable, the data comes to the Arduino, and in the Arduino itself, from the chip, it converts those USB data to serial data to send those data to microcontroller. Okay, so uh, but in our but when we are building our own microcontroller, like on Arduino board, like we didn't include this thing, no, the converter, USB to serial converter. So we have to like we don't design in our PCB right now, but we can use that USB to serial converter from outside. It's look like this. You can see this component. This is called USB to ASP converter. You can buy this. I think this will be around cost 400 rupees. Or otherwise, you can do the same thing, but the USB to serial converting thing using Arduino board. Like it needed, this need us to upload the code, right? And you know about bootloader concept, but I think you know about that. You can ask in the Q&A session also. Okay, this is for the uploading the code USB ASP. You should have either Arduino Uno or USB ASP. If you have Arduino Uno, you don't want to purchase USB ASP. If you don't have Arduino, you can purchase this one. So the FTDI is optional one. Like when we using USB SP, there is 6 pins: VCC, ground, reset, MOSI, MISO, SCK. There are 6 pins. It's very time consuming thing to connect six wires. But when it comes to the FTDI connectors, there is only like uh, uh, 4 pins, and it's easy to upload through the FTDI connector easily. But this is optional thing. Like if you want, you can buy this, but this is not a necessary thing. But anyway, we include this connector to our PCB. If anyone have, this is very easy. Here we are upload our code using TX and RX. Here we are uploading our code using SPI communication. Okay, I'm not going much deep in that content. I'll be directly go to the PCB and library, place 6-pin connector, place, and turn this and place here. Okay. Rename this as USB ASP and enter. And this connector, rename this as JST1. JST means you can see in my previous screen. This is the type of connector we call JST. You can either use headers, male headers and female headers. You can either use headers. Also, you can use JST. JST is much reliable. It made much reliable connections. Okay, we placed 6-pin connector and JST 5-pin. Then connect the JST 5-pin also. And rename this JST5 to FTDI and press enter, and U3 to JST. Okay. Actually, I need to, let's say, USB ASP. What are the connection? Let's see what are the connection. When it comes to the USB ASP, we need 6 connection. One is plus 5 volts, other one is ground, other one is reset, MOSI, MISO, SCK, right? So when it comes to the my microcontroller, you can see MOSI, MISO, and SCK in here, and reset is there, and ground and ECC like here and there. If we like, it's easy to me to connect. Let's say I'm going to this. Okay, like majority pins are here. Like it's easy to me connect from here. Like I can connect 3 pins here, and one is for plus, other one is +1, and other one is ground, and these 3 pins connected here. But this looks ugly if I placing like lot of things in here. Like already there are so many components. That's why I move these components away, and I will use a trick called net port. I make a net port, and you can again press space bar to rotate it, and you can place your net ports here. 1, 2, 3. I think we need 3 net ports, and here also we need the reset one. I place 4 net ports. In this circuit, we need reset, MOSI, MISO, SCK. Right? Here also MOSI, MISO, SCK. With the CB. MOSI, MISO, SCK. Rename this MOSI, enter. MISO, SCK. Other one is MISO, SCK. Right? And this is reset. What I do is I got this this, what do we call, this is net port. I place net ports here, and again I will place my, I'll be telling what does it mean when it comes to this PCB. It should be looks like reset MOSI MISO SCK reset CK. MOSI MISO CK. All right. What does it means is like I made two ports, like there is a net port calling SCK, and again there is net port calling SCK. What does it do is it connected these net ports without a wire. Like let's say this has actually wire, but without showing a wire, it will connect, right? That is the advantage. So my PCB is not getting any messy. So I don't see a wire, but there is a wire. That is called by net port. Making this connection with this pins and reset to this pin, and also reset to this. To this. Okay. Someone is asking how to find a net port. In the wiring tool, you can see a wiring tool here. There is this kind of symbol. This whole net port. You can get here and place it here. How can I replace? How can I place that reset label? Reset label is this one. It's just a net port. You can place a net port and rename it as a reset. Okay. Now you want 5 volt and ground. I click both and get copy and control B. And connect 5 volt and ground. Okay, I am done with my USB SP. I made all the connection here also. The another JST for FTDI. I'll be made connection also. That's FTDI connector needs TX, RX, and reset. I'll be connecting 3 net port. TX, RX is there, number 2 and 3. Get a net port. Rename. I want to tell you, like this is the RX pin of Atmega chip. You have to connect the TX again. You have to shift with FTDI. FTDI RX should connect with Arduino TX. FTDI TX should connect with Arduino RX. So we have to name according to that. Please make sure to name according to that. Here Arduino there is RX. You have to place TX here, and here RX to TX. You have to swap. Otherwise, the code will not upload if you swap those things. Okay, and here also you have to rename. Please rename the pins in my way, otherwise you will get a trouble. Like I place those names by looking at the uh, FTDI connector. There is the fixed pin, RX pin, and 5 volt and ground. So you have to place your pins according to that, right? If you lose the like flow, it will not connect, right? This is reset RX, and also we need 5 volt and ground here. Also, you can get select these two by Control E and Control C and Control V to paste. 5 volt you need. Okay. Again, you need a 100 nanofarad capacitor here. 100 pick go to the library and pick 100 nanofarad and place. You have to place here. Okay. And pick a wire and connect here. Connect to reset. This 100 nanofarad is for you can see it's connected with reset pin, right? If you are uploading your code to Arduino through FTDI, it need to get a common reference with Arduino reset. So along with that, we need to use a capacitor. I'm not going to explain much deeper in electronics because we are focusing on PCB designing here. So I am telling you how to place component, how to route here and there. Okay. Yeah, someone is asking about the USB SP again. You have to buy either Arduino or USB SP. You don't want to buy both, right? And the FTDI is optional. Actually, you don't want to buy it, but if you want to learn those TXRX things, you can buy. Right? සිංහලෙන් කියන්න ඒ කියන්නේ ඔයාලට එක්ක Arduino එකක් නැත්නම් USB SP එකක් ගන්න ඕනේ. ඒ දෙකම ඕනේ නැහැ. Arduino එකක් තියෙනවා නම් USB SP එකක් ඕනේ නැහැ. එහෙම නැත්නම් USB SP එකක් ගන්න ප්‍රශ්නයක් නැහැ. FTDI කියන ඔප්ෂනල් එක. ඒක අනිවාර්ය නෑ. ඔයාලට අරගෙන යූස් කරන්න පුළුවන් කැමති නම්. ඒක පොඩ්ඩක් අප්ලෝඩ් කරද්දි කෝඩ් අප්ලෝඩ් කරද්දි ලේසි වගේ වෙයි සමහර. වෙන ප්‍රශ්නයක් නම් නැහැ. Okay. All right. Please put a message if you are not unable, you are not doing this with me. Okay, we are done with the connectors. Now we have to make the power circuit. I'll be jumping to that. For the power circuit, we need to place 0.5 regulator. You can place it here. Okay. All right. Let's move to the power circuit. I place a regulator and the 0.33 microfarad capacitor here and 0.1 microfarad capacitor here. Okay. And then I have to place a LED and a resistor. I will go to resistor and pick place button and placed here, an LED place here. Right. We need input power, and we need the 5-volt output. Place it here, and we need a ground. Okay. Name the resistor to 330. 30 ohm. Get a copy of this. 30 ohm. Now connect those things together. Get a wire. You can connect all the components. This is very easy thing. I think you can catch up. I want to explain one thing here. Please don't make the ground overlap with this. Like if we overlap, let's say ground with this is not a good practice, right? This crossing. So please make sure to place 4-way connections in this way. Don't practice. And here also, either you can do this 5-volt connection here also, but you have to do beside that. Don't make 4-way connections. And this LED for like make sure your power output is working. It's not a mandatory thing, but it's good to have a LED, like it's indicate your power output is coming, so you can debug circuits very easily. Okay. We are done with our power circuits also. And okay. Now we have to move to our buzzer circuit. I'll be explaining some data sheet also. Let's say this is the data sheet of 7805 regulator. Not 7805. 7805 regulator. And here datasheet it's mentioned its output current up to 1.5 ampere. Like its maximum limitation, it's specified. And how does it look like, and what are the pin configuration, and also what in particular temperature, what is the maximum current, and what maximum voltages it can bear. Like here and there, you can go through your data sheet. I think in the Kitninaya sessions also, he will be go much deeper, like in how to read a data sheet. He will tell in his sessions also. Like you can see, like let's say there is a output voltage. You can uh, see the testing condition, and there is some temperature also, and it shows the maximum and minimum and voltages of the 7805 is typically it can like it can handle up to 36 voltages, I think 36 volt. Okay, and when it comes to the um, buzzer circuit, we need a buzzer, and there is a diode for protection, and there is a transistor and a resistor. You can see this presentation. This is the same thing. This is the buzzer and the diode and transistor and resistor. Like let's say we giving a PWM signal, on off signal, and then the transistor is on off, right? Like what we are doing is, like if we are directly connecting buzzer to Arduino, it will definitely like beep. It will definitely give a sound. But here what we are doing is, like if we are giving buzzer more current, it will make a bigger sound, right? And that's what we are doing here. Like we directly connecting 5 volt and ground with a buzzer, like through a transistor, and we are allowing buzzer to get a good current rather than Arduino. Like let's say in Arduino we are getting a small currents, no? So we are doing some sort of current driven. Like we are making a small we are like from a small pulse, like we are making a good current through our buzzer. Okay, uh, this is the explanation, simple explanation of that. You can go much deep. Like I will be explaining single also. Like ඔයගොල්ලන්ට කියන්නේ මෙතන වෙන්නේ බස් එක ඩිරෙක්ට්ලි අපි Arduino එකට කනෙක්ට් කරොත් ඒකෙන් කොහොමද Arduino එක බස් එකට සද්දයක් එනවා. නමුත් Arduino එකේ එන්න පුළුවන් කරන්ට් එක හරි ලිමිටඩ්. බට් අපිට ලොකු කරන්ට් එකක් බස් එකට දෙන්න පුළුවන් නම් බස් එක හුඟක් හොඳට නාද වෙනවා. එතකොට ඒ කරන්ට් එක දෙන්න අපි බස් එකට 5 වෝල්ට් එකක් වෙනම කනෙක්ට් කරනවා. අපි Arduino එකට කනෙක්ට් කරොත් ඒ ඩිරෙක්ට්ලිම එන්නේ නැහැ ලොකු කරන්ට් එකක් වෝල්ටේජ් එක තිබ්බා. ඒකින්ද වෙනම කනෙක්ට් කළා ඒක through ලොකු කරන්ට් එකක් ඩිරෙක්ට්ලි ගන්නවා. ඒක ගන්න ස්විච් on off කරන්න වගේ තමයි මේ ට්‍රාන්සිස්ටර් එක යූස් කරන්නේ. ඔයගොල්ලන්ට තේරෙනවද මෙහෙන් එද්දි මේ පාත් එක කනෙක්ටඩ්. Okay, we will directly jump into the circuit because we have limited time. Okay. Buzzer. 5 volt buzzer here. Place. Pick the place button. You can place here, and you need a diode. Actually, you don't need this kind of circuit. Like you can directly connect buzzer to a digital pin, and on and off you can get a buzzer output. But we are doing some little bit advanced thing to like get a small knowledge regarding that. And you can place a transistor. This is BC547B NPN transistor. You can place whatever NPN transistor. This is the common transistor, and you can place a resistor also. And we need 5 volt and ground. We can get a copy here on here. Okay. in the buzzer, please move the text because it will distract with the line, and rename the buzzer with LS1. LS means please rename with LS1. Okay, then diode, it's 1 in 4001. Resistor, it is 220 ohm. I can get a ohm symbol from here. Okay, and yeah, PC 4547BC now. This is less in text, and you can make the connection now. Connect the ground to transistor, buzzer 5 volt. Connect the diode. And connect the resistor. Okay, and then we have to connect the buzzer. So let's see what are the pins that we can plug the buzzer. So we have to plug to the PWM pins. So PB3, PB2, and PB1 is PWM. Yeah, the PB1 also a PWM pin, so we can use that pin. Okay, you can check with the Arduino pinout. This is PWM pin, so I will use PB1. So you can place a net label here, and you can place another net label here, and rename as buzzer. Get the name closer. Rename as center. Okay, and then make a connection. All right, and we have to do another circuit. We have to place a LCD circuit, so that we need the phone. Go to the library, pick just the 4 pin, and place. You can place anywhere. Place it here, and move those things down. SCL SDA 5 volt and ground. I will pick this thing. SCL SDA 5 volt and ground. CL SDA, and get a copy of 5 volt and ground. I will make a copy here. Control C and Control V. Move the ground closer. Okay, and you can make the connection. This is for our LCD display. All right, and let's mark the LCD connection on our microcontroller SDA. Get a net port, type there. This is SDA, this is ACL. All right. Close. Then we can connect. All right. We can rename this as JST3 already. LCD. Okay. All are good. The naming is all right. We are near to complete. I want to know you are up with me. And I want to give you some small clarification regarding the LCD circuit here. You have to purchase a LCD display. 16:2 display would be enough. And also then you have to buy a I2C interface module. When it comes to the LCD display, there are so many pins, right? Like if you don't use this kind of I2C interface module, you have to route all the 8 to I think 6 to 8 pins. We have to route all the 6 to 8 pins to our microcontroller. Like it will be like a big messy thing. Like to reduce my wires, I use this I2C interface module. You can get those things from electronic shops. And there are some modules like they already attached to the attached the I2C modules to display also. There are some this kind of modules also. You can buy it as well. And then we have our last circuit, push button panel circuit. We need 4 push buttons and 4 resistors. Let me go there. We have to connect SCL and SDA. Okay, SCL in microcontroller. Our microcontroller at Mega 328P is PC5 SCL. Other one is PC4. Number 27 and 28. 27 is SDA. 28 is SCL. You can go through the. Let's simply search at Mega 328P pinout, and you will get a photo, and you can see what is the pin of SCL and SDA. Okay. Let's get a push button here. Push button and place it on your PCB. 1, 2, 3, and 4. You have to move this your microcontroller circuit a little bit upward. I know this way. And you need to place 4 resistors. 1, 3, and 4. It will automatically name, right? So name these resistors as 4.7K. 4.7K. Okay. Then we need a ground and VCC. VCC not VCC. 5 volt. We can get here. Control and control copy both and paste both. Place ground here. I will place 5 volt here. Somewhat here. Okay. Then I need connect this button to my Arduino. So I use net label, rename as BTN1, copy, get a copy, get a copy. I'll be renaming as this one is BTN2. BTN means button, small name I will give. This is button 3. Move it closer. All right. Get a copy, and you can connect any digital pin your button, right? So I will choose these 4 digital pins here. I choose because they are like in here, right? So if I placing here, it will be easy for me. Other than this, if I placing here, it will kind of messy. That's why I choose here button 1, button 2, button 3. Please rename the buttons and make the wire connections. Connect to here, to here. Okay. Let's move some. We have to first connect the resistor to the push button, and then we have to connect the button. So I move the button connection away. Okay. All right. Now I get a wire and connect this thing. Connect these two. These two I will route to the ground. Connect these two. Connect to the ground. I connected all the push button to ground, and I will connect it to button as well as resistor. I will also I think you are following me. This is very easy thing. You can follow the slides if you want. If you need to see the connections, or you can see my screen as well. Okay, let's see. I am done with my buzzer circuits also. Okay, I think you are with me. I will explain why we are using resistor here. Right? Here we call this resistor pull-up resistor. Right? Let's say this BTN1 connects to the Arduino directly. Arduino means microcontroller directly. So the BTN one, we read the signal from that button. This port we read the signal, right? The push button. No. So if we are pressing the push button, it will connect this point to ground. Otherwise, it will connect to 5 volt, right? It's always connect to 5 volt. If you are connecting, if you are pressing this push button, it will connect to ground, right? That's what it happened. Like what we have include this resistor is to to avoid directly connecting the 5 volt and ground. If the 5 volt and ground directly connecting, it will like short circuit. No, it will like burn it up. Okay. To avoid that, we include 4.7K resistor as a pull-up resistor. Pull-up means it's pull up, right? It's pulled up high voltage, right? It's always 5 volt there. If we press the button, it gets 0 volt, right? That's what it happened. Okay. This is the copy of the 4 circuits. All right. Now I'm there. Battery. We need the simply to connect. You have 3 options. First option is 1.5 volts. You need 4 1.5 volt batteries. So you can make a 6 volt here. So you need 5 volt. No. So for the regulator, you have to input a high voltage than 5, right? So you need to get you need to get at least 6 volt. That's why you need 4 batteries, 1.5 volt. Or you need a 9 volt battery. Or otherwise you can buy a lipo battery is something like to this, and you have to buy a charger also if you are buying lipo battery. Or you can buy either rechargeable batteries also. There are some 1.5 volt rechargeable and 9 volt rechargeable, and also in the parallel to that you have to buy a rechargeable charger also, right? um okay, let's make this connection. This is my last thing to do. Go to the library, pick to JST2 pin and place it here. You can place this way. Oh, let me place it again. Place it here, and this is JST4, and let's name it as power. Okay. And we can connect VCC here. We can connect ground there. We can connect. Okay, I think I have done with my circuit. There is one little thing to do. There is not using pin, right? In Arduino, 6 pins. Let's take a cross thing here. In wiring tool, you see on there. This is a good practice. If you are not using any pins, you can place cross here. Okay, I think we are done. We are done this schematic. Congratulations, I think you have done your schematic. Someone is asking, can we connect our Medibox to main power through a power pack, which we can get reduce our output voltage 6 volt. Yeah, definitely you can. So if you are using power pack, there is some jack ne. So you have to place a jack. You have to find the library power jack, and you can connect. You can import that jack here. So you have to buy a jack from the electronic shops also. You can do it anyway, like right? Either you can connect to 230 voltage also. You have to get a bridge to like transform or something to drop down the voltage, and you have to do a lot of things if you are using 230 voltage. But we are recommending you to use DC voltage since you are very beginners. Okay, I will be telling you how to place a box. I think you have seen that I have placed box in my PCB and it looks nice, right? In the text with box, it looks nice. So I am telling you to do that. I'll be not placing all the blocks. Simply go to drawing and here there is rectangles and press escape button and click on the rectangle, and here um, you can see stroke style. It is on solid. You can set it to dashed. Okay. If you want, you can change the color also. Like if you like change the red or something like that, your choice, right? I'll be choosing red. Place a text also. In the drawing, there is a T shape and it's for text, and you can place a text and press escape. This is a LCD connector. Right. If you are selecting that text, it will appear the text attributes. Attributes mean you can. I want green color. I put a green, and you can select a font and font size. I will reduce my font size up to 7, and it will reduce it. Whatever. There are so many options. You can try it out. Let's. No, it looks like green. I don't know it. So let's make it black. Okay. Now it looks nice, right? You can like choose any color. Either you can choose this border as also black. Up to you. So I'm done with my PCB. So please do. I'm not going to draw the all the the rectangular shapes everywhere. You can draw and make it clean like my PCB. Like my PCB, I previously drawn this. We were there. Okay. Now you have done a very good job. And please control S, press the control S to save. Otherwise, you will lose your project web. Please control S, and it will connect into the server to save the project. And since my internet connection is a little bit slow today, it will take little time to save. In the meantime, I will explaining what is the PCB layout. So we are done with PCB schematic. The PCB layout is a high-level engineering tool for design of the PCB. This is the PCB layout. How does it looks like? Layout is basically we are connecting the components. Like in the schematic also we are connected, but there is not defined proper connections. No? So we are here. We are setting the defined paths. We are drawing the paths. That's what we do in routing or the layout. So there are so many features. I will be explaining the PCB features with you for you. So first one is placement feature. You can place this PCB in the previous one. I told you about symbols. Symbols is someone like the rectangular shapes, and here there are actual symbols, actual shapes. We call them footprints, right? So we can place footprints, and we can do manual routing. Manual routing means we can route by ourselves rather than letting it to do software. This PCB layout features, another feature is high-speed auto router. Like in the software, there is auto routing feature. Like it will route automatically. Like there is a feature in ECD also. I think my project is saved. And I will show you in the PCB layout session about the auto routing. It's routed automatically, but it is not good thing. I will tell you why in the future slides. And also another layout feature is manufacturing output. Like I told you about gerbers, and we can generate gerbers through layouts, right? So it's another feature. And also we can import and export. We can import 3D objects like this kind of cylindrical capacitors, IC shapes, and headers. We can import, and also we can export 3D outputs as well, right? And there are some advanced verification features, like they are checking like we have what we have done, like are we done correctly or not. They are it's called design rule checking. And here is the initial look. If we load our layout, and this should be our final look, this should be our target, this is our initial route, right? Okay. I will be explaining what is PCB library. I explained about schematic library. Schematic library, this kind of thing, right? So the footprints here, PCB library or .pcb lib. PCB lib means PCB library. This is the extension of that library, right? It's called footprint. Let's say this one. This is a footprint. There is this is the actual shape, actual placement of the this component. This is the physical pad arrangement. Actually, footprint is physical pad arrangement. Actual, how does it actually looks like, right? We can attach 3D objects to that also, right? This is what footprint means, or PCB library means. And we can attach 3D libraries using step files, okay? And then there is another thing called integrated library. Integrated library is its extension is .int lib. Again, integrated library, okay? Integrated library means it has like let's say you know about zip files or R files. What does zip files do? It's compress all the things and make a one file, right? This is also the similar kind of thing. This integrated library makes schematic and PCB library get together and compress it and make a final outcome, like as a zip file, same as a zip file, right? Integrated library means combination of both schematic and PCB library. You can see this is an example of integrated library. This is our schematic, this is resistor schematic, and this is layout, and this is 3D also. This is, all these together we call it integrated library. And one biggest advantages of integrated library is it is portable. Like everything is in one file, right? We don't want to have separate file. Let's say in this projects also I give you 17 different libraries, right? So if it's easy to have one library, no, without 17 different libraries, so it's easy to have an integrated library. We can portable, like we can travel it anywhere, and very easily. And when we make an integrated library, no one can change, no one can make modifications in the integrated library. So if we want to make a modification, we have to extract, like in the zip files also we are extracting them, no, to look at what inside them, no? So we have to first extract them and we can do changes to that. And also in integrated library we can integrate up to 70,000 components to one integrated library. This is advantages of using integrated library. Here in the ECDA, we are not using integrated library. I told you, we are directly importing them through the internet. It's very easy and convenient. But if you are using a software like Altium, you have to use integrated libraries. Okay, I'll be moving to my PCB again. Now you have to there is a design you can find in the top of your browser in the tab. There is a design tab, and here you can choose convert schematic to PCB. Okay, if you click that, it converts PCB to schematic, and it will pop up a window also. it asking to choose a unit. Please remain as millimeter. If you want, you can choose it inches. Millimeters is good. And let's say 2 layers is good, but we are doing a 1 layer PCB here. And board outliner rectangle is good. Start with, let's say, 0 and end with 80. With start with 0 and end with 80. 80 is a good, I think we can manage from 80 means 8 centimeter, and you can apply. Please. Oh, sorry. Width is 80. Starting means origin. Give them both 0 and height to 88. Okay, this box will appear. Okay. Now you have the components and your box. The box is your PCB like area. You can anyway change. You can click on that and drag it here and there, right? You can change the shape. We can change the shape in the end. And now we have to place, right? The placing is the critical thing, most critical thing in PCB layout. Like 90% of the focus should be on placing. After that, we can route 90% placing and 10% routing. It's the principle, right? Someone is asking how to get the PCB layout. You can go to your schematic again. There is Medibox schematic, and in the top tabs there is design tabs, and you can choose convert schematic to PCB option. Then it will automatically generate this one, right? Okay. First you have to save this. It will save PCB Medibox project like that. Okay. Then you have to place. So the most critical component is IC, right? So I will place it first. Okay. Then I will be looking to my schematic again. And I will be first placing the crystal oscillator. It's very easy thing, no? It's near to the IC. So I'll be getting crystal oscillator. This is my oscillator. Oh, let me see. This dot indicates the first pin. My IC first pin should be on this corner, right? This is rotated. So please click on that and press space bar to rotate here to make the dot on left top corner, right? So your first pin appear on here. Reset pin, your reset pin on your schematic also on there. This kind of here, right? If you are looking at Mega 328P chip, you can see the pin number 1 is there, right? Pin number 1 is there. 1, 2, 3, 4, 5. Right? So you have to place your components according to its physical appearance. So this is the correct way, and then you have to place the crystal oscillator. Now you have to think, if I'm placing this oscillator on this side, it's harder to route, right? We have to make a route connection from the round way. But if I make this component in this side, it will easy, right? It will easy. So it made short connection. But now look, this thing connected to this, and this thing connected to this. What do I have to do? I have to click on that and rotate it. All right. Okay. Now I can easily route this component. Okay. You got the idea, I think. Okay. That's why I told you the placing is most critical thing, right? Placing is most critical thing. You have to do 90% of, you have to allocate your 90% of your time to placing, and this is a thing that your brain involved, right? You have to think very intelligently to place components, and you have to place here and there and rotate here and there. And this is a very very funny thing and very like awesome thing to do, right? So I think you will like to do that. And this is very interesting, right? So right, okay. Then the text, you have to bring the text on the top, and you can rotate the text also by placing spacebar, right? This is U1 component designator. It's better to have it on the top. Rotate it. Okay, I place it. Now go to the schematic and look what we can do now, next. We have 2 picofarad capacitors, right? To connected with our crystal oscillator. Right. So let's see what are the designators C1 and C2. Okay. Okay, then move to the PCB. Here are they, and get them closer to this. Okay, let's say if I place my C2 here and C1 there, it's maybe a hazard, right? Like we can't route like we can route, but it may be a long connection and some messy things, right? Here connections are here and there, so we have to make closer to this, right? C1 on here, C1 on here. Let's say you place C1 here and C2 here. What will be happen? This C1 connected to this pin, C2 connected to this thing. So how can we make a connection? Let's say I put a wire. This is the PCB wire track. We told track. We can route this one, right? We made a connection, right? So how do we route to this? This cannot route, right? I can't go like crossing another connection. So I have to go like here and there and go to connect this, right? So this is very not a good thing to do, right? So we have to think intelligently to connect these components. If we place like this make easy, right? We can easily route. Okay, I think you got the idea. I'm not going to place all the components. I will let you to think, right? We will be giving you a week to think to place these components. You have to think intelligently and place the components, right? Okay. I will be telling you some best practices and how to do this thing, and you have to do your own. I will be giving you time, right? Okay. Let's say this one, buzzer. Buzzer is also same. Buzzer is connected to this 5 volt and not buzzer. Buzzer, when it comes to buzzer circuit, it has another component connected to it. Let me see. Yeah, it's not directly connected to the this microcontroller. It's a directly connected component. Let's see. This one, FTDI connector. FTDI connector, it's connected to RX, TX, and reset. Okay. Then let's see where is RX. RX and TX on the 2 and 3 pin. Right. Now go to your PCB. Let's see where is RX. RX and TX there, right? And reset is there. So it's good to place this thing here, right? It's easy now. If we placing this way, it will very hard to route, right? Not disconnect. This is a CLSD thing. No? It is LCD screen. So we have to choose TXRX, this one, JST2, and place it here. And okay. I'll be getting the text on the top and rotate it here. Now this thing will easy, right? So we have to first place the components here and there, and we can place this thing over here, some sort of here, right? Because SCL is here and SCL we have to connect there, SDA here, SDA there. Okay, and we have another connector. I think you can remember this is our USB-SB connector. It has MOSI, MISO, SCK, and those things. Let's see where those things are. SCK is there, MISO MOSI there. So we have to, it's better to place it here, right? Okay. Now I place some components here and there. Now I will take a wire. This is we call track, and you can place the routing layer. Please stick on top layer because we are building a one layer PCB, not two layer PCB, right? So please stick on one layer. So you can pick a wire, and then you can click here and click here, it will connect. Click here and click here, it will connect. Click here, let's say I will connect here. This way. Let's see. I am connecting with 90 bends, right? This is not a good thing to do. Like if you are routing with 90 bends, it has a very electronic side disadvantages also. I'm not going to telling you like much deeper. Like there is electrons like on the corner, and it will like there is so many things to explain. But you can remember in the end of the takeout message is don't use 90 bends. So you should always use 45 bends, right? Pick a wire, and here don't use 90 bends. You can use 45 angle, right? This is 45, and go here and here and here. All these are 45 connection. There is no 90 bends. So this is the one thing you have always. First thing you have to do is there is in the design tab, there is design rule, right? In the design rule, there is we can set track width and clearance. Clearance means the minimum distance between two tracks or two components or like that. We can set those things, right? So and diameter, so and so. Don't change this right now, right? Don't keep it as same. Like let's do some sketch routing first. Sketch routing means make sure all these things we can connect together, right? Like first try to route using the default thing, and then you can change the width. Like let's say you are manufacturing this PCB on. So if you are manufacturing your own by using ironing method, you have to like you have to let this thickness much as wider. So let's say if this if this track thickness is very small, like if you are doing some ironing method or something, this track will easily damage. So you have to make the tracks with bigger as much as possible if you are doing these PCBs in your own. So we can look into that in our final stage. Let's do some sketch routing. Like first you try to connect all the components together, right? You can route, get a connection and pick and place here and there. You can make a connection, right? So these are the basic things. After you done your sketch routing, like, and you can make some design rule change, and you can route the PCB, right? Okay. I will let you to like I do this your own. Like you have to use your thinking capability to route, and of course there you don't be missing anything because uh, I routed it already now. So the slides also available. You can see where I put my component here and there. So you can exactly place those components in there and route according to that. But I am suggesting to you like don't look at my slides and put it your components here and there. Try to build your own way, like trying to use your brain. Let's say you can build better than me, right? I did only in one way. You can route better than me, right? So that's the one thing I wanted to tell. And another thing is, let's say um, I'll be explaining this. in my I'll be logged into my finalized PCB right now. Okay, this is my schematic. You can build this your own, right? You can name your schematics, and then this is my final outcome. I will delete this thing, and this is my component placement. Like, try to do it your way, right? So I place these things and routed those connections, right? Like, if you are done with routing, this should be your finalized look, and you can see there is some special things. What does this mean, right? Let's say I will be deleting this connection now. Right? Okay, now I routed, right? I have a problem. I have a problem. What is, I have remaining one connection. How to route here to here? That is the biggest problem I have faced. I route everything, but there is remaining connection. I couldn't do. So what can I do? How do I route to here to here? So let's say I want to route. I can get a wire, and there is no way to go. Right? All things are blocked. I can't route anywhere. So I am using a trick called there is a VR. VR means we are connecting. Let's say there are two layers. One is top and one is bottom. We are connecting top to bottom. So I am routing. Like uh, I'll be explaining you while I am doing. Let's say I want to route to here to here. I am in here. I will place small wire and escape, and here I will be placing. No, let's say I will be telling you in an easy way. Like I want to route here to here, but in the top layer, I am in the top layer. There is bottom layer and so many layers. Top seals means the yellow color thing, right? The names and all the component borders are in the yellow color. So I want to route here to here. So I am using a trick called VR trick, and this one I am using bottom layer, and I am let's say I am using a wire, and I will route here to. Don't make 90 bends. So I routed using a bottom layer, right? So then what you have to do is you can place a VR on both sides, here and there, right? So you can increase the width also. Let's say if I pick I can set a diameter 1.3 or something like that. This one also I can set a hole size. I said 1.3. I will set 1.3 and drill diameter is drill hole 0.9. Okay. Okay. Now you can you can see, right? You can see the whole line is divided to 3 parts. Right? So now you can change the layer. Here the problem is here as a middle red line and change the other things to red. Okay? You can pick this line. We can set to top layer. Or otherwise we can delete it. Or we are selecting top layer and pick a wire and place here to here. Okay. Now also you can delete this thing and you are make sure to in the top layer and pick a wire and you can route here to here, connect to here. I think you got the tick, right? I think you got the tick. The problem was I can't go, I couldn't go here to here. So I use a trick called the layer changing. I use bottom layer to route here to here. I routed it and I place VR on that. I place 2 VRs and I make the VR bigger, and then it will automatically separate into 3 parts. Then what I did was I delete the blue color part here and delete that and reroute it using top layer, the red thing. So now my PCB looks like that. I will be go. Okay. Okay, I think that was the one tricky thing I have found in that PCB. I think from that you can do this. And also another thing is placing the mounting holes. You can simply get a pad. Let's say here is a pad. Pad is a hole. You can place here. And mounting hole means like it doesn't need a copper thing around that. So you can let's say your pad diameter is 1.6. Diameter means here to here length, and make the hole length also 1.6. Right? So there won't any copper thing around it. Here also, let's say here is a component hole. No? So there is this one is hole. There is no copper connection. I removed that through this hole size making similar to the width or height size. So that's the another thing that I want to tell you. Okay, after doing all the things, you have to like if let's say you have done sketch routing, so then you can make the critical things bigger. Let's say this is the power thing. It's better to like make the power width higher. Let's say now you have with call 0.9, you can make 1 point, let's say 1.2. Press enter and it will make bigger, right? So try to make power path bigger, right? So it's easier to like make big paths. Let's say I routed every path as 0.9 millimeter. It's better like if you are doing in your home manufacturing, like it's better to the parts are big. But if you manufacturing from China or whatever PCB manufacturing company, it's okay to it's so smaller, but there are some minimum capabilities also. I think 0.13 is the minimum thing in JLC PCB also, minimum track width, the width of the track. So I think you have to understand that. After you completing your the routing thing, you can make. I told you can make your connection. I got 2 difficulties like as I explained the VR connections, and please make sure to place a name like this. Like I placed 2 VRs, so I made a name here. I made a text and I made a name here like jumper 2 and jumper 2. What we are doing is like we are building one layer PCB now. So one layer, but we are some discontinuity. What we are do here is we are connecting them through a small wire. Like there are two holes now, so we can connect to these two holes from a small wire. This is called jumper. So those two name as similar name, jumper 2, jumper 2. There is another connection, jump 1 and jump 1. So you can make connection as like this. So think to route intelligently. You can, I know you can do better than me, right? So okay, the final thing that I have wanted to tell you is placing a copper pole. Before going to that, you have to go to your design and design rule and make clearance bigger. Its default come with 0.1. Make this clearance with, let's say, 0.6, whatever you need, and press enter and press save. And it will take small time. Okay, got saved. And here you will see solid region button. This one, this shape, solid region. Pick that, and you should have to pick your four corners. This corner, and then pick this corner, and pick this corner, and pick this corner, and pick this corner, and click right click, and it will apply the copper pole to that, right? Sorry for that. I had made another copper pole here, that's why it's got double. Design rule, okay, settings, and control save. And you have to pick a copper pole and do it like perfectly. I will be like, I'll be telling you the method, but you can try and click right click and it will appear. Mm. Sorry. Let's make. Seven. Mm, I think I got some connection, but it should be work in this way. Yeah. If you got any trouble, like please let us know. We will like we can go through your PCBs and let your problems. And you can also learn from these things like ECDA, Popo, and this tutorial saying how to place a copper pole. Like I follow the exact similar things. Me show it. Like This one. Before using copper area, please make sure your PCB has close border outline. This one. Hello, අයියා පොඩ්ඩක් continue කරගෙන යන්න පුළුවන්? My connection drop වුණා. අයියාගේ ටික පොඩ්ඩක් continue කරගෙන මම ටක් ගාලා ඉන්නවා. මේ current එක ගියා ඒක.
Okay. Sorry for the technical difficulty. There's some power issues. So Dilanka was talking about the copper pole section, and I think you can refer to that guide he shared. Let me get back to the.
Am I audible?
Yeah, you're audible.
So I can finish my part then.
Is the screen working?
Yeah, let me share. Can you see my screen right now?
Yeah.
Sorry guys, I got a power cut. I don't know. And here this thing, you have to pick this one, copper area thing, and it will ask you to connect your nets to ground. Please set it as a default ground and make the area, mark the area. And press right click to mark the area. Okay, it will mark. So the reason why the copper pole has this much, because of my design rule, I set the bigger, let's say I set 0.6 settings, and I can reload like import. Let's say what I have done was let's say we pick a line and get a ground connected. And it worked, right? So so I'm sorry, this is not the option. Solid region is not the option. The copper area is the option. Please choose that. My mistake, my bad, sorry. No, this option is not the solid region. This is the copper pole option. Select this copper area and set this to ground, and before that you have to set your design rules, right? So please make sure to set a bigger gap between copper areas, right? So this will copper pole, like the copper pole means the copper area between components. So now you have a finalized PCB. So let's say you want to add the image to your PCB. Let's say you want to add a photo. I will be at let's say design in Sri Lanka, made in Sri Lanka, and I will be set it to 1. Even you can add your image also. So I have to move to the top silk layer. So anything you can add, even your name, anything, right? You can place a text also. This means you can place your name. I place my name, Lanka. Right? You can change the font size, font color, anything, right? So these are the things that I wanted to tell you. So I want to try yourself these things, because these things we need to focus on our brain and focus on the things to place here and there and route it properly. I told every tricks like don't use 90 bends. I want to tell you again, don't use 90 bends. Please place component intelligently, and then you will be facing a problem called this going through connections. Like you can't go in through like you can't crossing red in another red. So I used a trick called the layer shifting. I shift the layer and I routed the connection, and then I place the via on that, and I separate the parts route it again. Blue means for the blue thing we have to place a jump wire on that. Okay, in separately after manufacturing PCB. So that is the things that I have. Those are the things that I have to tell you. Like you can like move these things anywhere like as you want. If you have any problem, please contact us. And okay, those are the things I want to tell you. Back to my slides. I will go through this very quickly. And this is the cross section of actual PCB. PCBs looks like that. And there are seal screen, solder mask, copper, and substrate. This is the substrate. Substrate means the in between area, the material. It's almost fiberglass. And we have a copper layer. From this copper layer, the connection are made by this copper layer, right? And then the solder mask is the green layer on top of the copper layer. It's a protective layer. And seal screen is the, you saw in our PCB, the yellow color things, the names and the border areas are seal screen, right? So this is the general idea. And to get familiar with the terms, the trace is something, the copper part. The annular ring is something, this resistor, you know, there is some around the hole there is some copper area. This is called through hole component. We call it annular ring. And VI is, I told you earlier, to going through one layer to one layer. VI is a hole that connecting two layers, right? The pad is something like you know, if we have SMD components, pad is the area that we can place the component, right? That's the idea of the pad. And DRC means design rule check. Software tool, like let's say there is also design rule check. Design rule check. If we checking design rules, if there is an error, it will pop up with the errors, right? While checking, I'll be go through my slides again. And it will design rule check, basically going through your path widths, and it makes sure your PCB is correct or not. And then you have two things: through hole was a surface mount kind of component that it have a lead, and it go through a hole. We told it through hole. And surface mount is we solder those components in surface level. It has a pad, this kind, right? You can get the idea of this thing also. This is a through hole, this is surface mount. And PCB routing, when we routing, PCB is 90% of placement and 10% of routing. And there is auto routing option as well. In your ECD also, let me close this. There is auto route option, but mostly it don't work, because ECDA auto router mode will host on a server. Like it's really busy every time, because there is one server, and let's think all over the world people are connected to that server. The routing things like makes a lot of time. Like let's say for the simple circuits also, it can make like 6 to 7 hours maybe. So there is option called auto router. You can install local router. You can click this option and download the routing software part to your laptop and route locally through that if you want. But we don't recommending auto routing. Please do manual routing. Auto routing is not reliable thing to do. Even though it's not reliable. And there are some manual routing tips. I told these things also. And we have to understand the manufacturer's specification. I told you about that JLC PCB. There is some minimum length they can manufacture. So we have to think about that before going to routing. And we have to leave enough space between traces. Otherwise, the traces are overlap. And the next thing is we can figure out trace widths, and there are online softwares that you can calculate. Like let's say you want to have a 1 ampere current path, and you can calculate for to going 1 ampere what width and what height should that copper path should have. Like you can Google search what are the PCB trace width calculators, and there are so many calculators. We will be explaining those things in our next session also. The best practices part those are the small introductions. And the next thing is always we connect all these things to ground, like right. Let's say this PCB also, if you are clicking that, it asks us to connect all the nets to ground. All the nets means the common nets. So these big areas are connected to ground. So this is very good thing, but there is some disadvantages also. Like let's say this in between these copper path, this copper pole is like working as an antenna, but we have to reduce that. To reduce that, from the design rule, you can make clearance bigger. If you make clearance bigger, like it will make big clearance between two copper paths, so it will reduce antennas. So that's the thing. That's the one thing I want to tell you. And another thing is, I already told you, avoid using 90 degrees. You can see from this GIF also, it's avoiding 90 degrees, and it's always routing through 45 degrees part. 90 degrees are okay, but we don't recommend, but there are some issues. Better things is 45 degrees. It's very easy. Curve path is better, but it's easy as to do a 45 degrees path. And next thing I want to tell you about gerbers. Gerbers are, I already told this idea in my previous slides also. Gerber is something we can generate through our layout. Here we can file, export. Here there is a generate PCB fabrication files. From the brackets they are specifying gerbers. So by clicking that, you can download the gerbers directly, right? So gerbers is something like this one. Like one gerbers has 6 files. One is having the board. The one is having the component outlines. One is having the drill holes. One is having copper paths. Like that, it separates those things. And gerber is somewhat the machine wants. Not that's not want us. What we want is layout. But machine don't recognize layouts. They need paths separately, pads separately, and borders separately, and so and so. So those are this is the simple idea about gerbers. Gerber is an open 2D binary vector image format file. This like this may be high for you, but this is a simple idea. Get the simple idea. And this is 3D visualization. Let's say my PCB. There is option in 3D. If you click that, it will generate 3D visualization. And my components are like not loading due to my internet connection, and this is not saved yet. That's why the reason. If you are clicking that 3D, you will be getting this kind of 3D view. So you can, it's automatically generated because I already attached these 3D files to my libraries. So it will automatically generate this kind of 3D for you. Yeah, those are the things that I have to tell. And the one more thing, you can make your submissions. You can complete your PCBs. I told everything that you want to do. Please route your PCBs and share with us. This is a submission link. You can scan the QR code also. This is a Google form. You can fill the Google form, and there is a option in ECDA in the file. Not file. Here also there is option called share, and here also if you're right clicking on here, there is option share. If you click in that, it will generate a link. You can get a link and paste it on our Google form and send to us. So then we will be going through that and send you feedback. If it is your PCB is correct or not. Okay, share your design on Facebook with the hashtag. You can actually share your final designings. Like let's say this is my design. So you can build your own designing. You can change these colors very easily. There is a drop down menu here. Here also you can change color. No? Likewise, after building 3D body, you can change the 3D parts color. So after completing that, you can post your design in our Facebook embedded by this hash code #embedded system #SLI #PCB design workshop. And this is my PCB. How does it look like? I manufactured this from Sri Lanka. We will be telling details how to manufacture and what are the manufacturing methods in our next session. Please join to learn how to manufacture PCB to our next session. And this is how does it look like after soldering. Okay. Now I will be handovering the session to continue to Kitminaya. Kitminaya, over to you.
Thank you, Dilanka. You can see me, right? And I'm audible. Okay.
Yes, sir.
Thank you very much. And I hope all of you had that wonderful time learning about PCB design from Dilanka's session. I know that there were a few technical difficulties, but the information or the knowledge that you gain from Dilanka's session will be really valuable for you guys. And I have sort of a small session plan for all of you to sort of guide you on how to use that knowledge that you gain from Dilanka's session to do your own microcontroller PCB designs. And since we sort of bit late on time, I'll finish this session really quickly. But if you have any questions, please send them to me so that I can further answer them. And always keep in touch with us. So yeah, so the Medibox is done, and now you guys know how to make your Medibox. But this knowledge that we are giving is for you to develop all kinds of microcontrol projects. So you can use your Arduino chip to develop any kind of project, right? So here we're going to consider an example of how to build a micro mouse. So a micro mouse is a small robot that is like very small, so size of your hand, smaller than your hand even. And you can see that it's very fast and extremely fast robot that is built to sort of solve this kind of a maze. And it's using different kinds of sensors and different kinds of motors and algorithms to solve this kind of a complex maze, right? Now we have like sort of introduced a few steps, general steps that you can apply to make your own micro mouse. And these steps are also valid for any kind of a microcontrol project. And let me introduce you to this general set of steps. So first step is you have to look at what is available online and choose your design. what you're going to build, what it looks like, what kind of things you require for it. So you have, once you have a topic, so if you're going to build your micro mouse, you have to look online for available designs and information. So these are some types of micro mouse: two-wheeled ones, one-wheel robots, this space in the middle of it, those kinds of things. So yeah. Now, second step is you have to look at the available schematic designs. And there are many different kinds of circuit designs. And sometimes when you can't come up with the electronics on your own, you have to like get ideas from the internet for like available designs. And then you can start to learn about the electronics on your own by looking at those example designs. You don't have to copy these designs itself. You can use these ideas to make your own design, and that is very important because it has to be your own thing. So some of you might even build your own Medibox projects using the information and the knowledge Lanka passed on to you. These resources are also available in this link I've given below, so you can go there and read further. So the next third step, which is a very important step, and it takes a lot of time. You have to be very careful with this step, and it's very time consuming, but it's one of the most important steps. And if you do it properly, you will end up with less mistakes. Because like in the Medibox project, we guided you through the project with our experience, and we made sure that you didn't have to face any mistakes. But for your own projects, you might have to do it on your own. So you have to reduce mistakes as much as possible. We'll be introducing more techniques next week about how to deal with those kinds of things. So here, data sheets are the best resources for you to make sure that you're doing things correctly. Data sheets have all the information you need to build your circuits. And it's very important to use data sheets and to learn from data sheets. So these are like examples of what you would need if you are going to build a micro mouse. So in this article we provided, there's a lot of information on this article here, a lot of information on what kind of data sheets you will be referring to when you're going to start designing. So third step, you have to start designing your circuit. Now here is the circuit of the micro mouse that we have designed for, and we are showing in this course actually. And we've selected the microcontroller. So that's our embedded system, STM32F407. It's a chip. It's the embedded microcontroller of a micro mouse, the brain of the micro mouse. And we have all these schematics like Dilanka introduced us to different kinds of components, right? How to build these kinds of things. So this is what the micro mouse's schematic looks like. And this is the programming one with all those SD, W, WCLK, those pins for programming. Those also you saw in the Medibox project, right? Microcontroller, STM32, motor controller, gyroscope, power system, very complex power system, not like our Medibox, and transmitter receiver circuits to detect, like you saw here, that micro mouse is detecting these walls and receiving, sending signals, receiving signals, and reacting to those signals. So those circuits are here, and LED mode for like user control, right? So this is a typical micro mouse, very complex one, but all of you can do this. So this is the, what I'm introducing is the step-by-step procedure for you guys to do something like this. Step 4, start drawing your microcontroller PCB design. Now I have for step 4, sub-step 0 I have introduced, but I've marked it 0 because this is step 1, but this is 0. Why? Because most of the people who design circuits sometimes do not consider step 0 first. But for me, step 0 is probably the very most crucial step, because you have to come up with how you're going to design before you start drawing the circuit on a square, what if you want to design something that is not a square, maybe a circle, maybe some odd shape, like you can see the shape of the microcontroller here. So just first sketch down what kind of design, like based on the online research you did in step 1, you have to decide what your shape is going to be, what kind of if it's an alarm clock, if it's some kind of a sensor you're going to fix to the car, it has to fit some kind of, like on the door maybe, has to have some kind of a shape. So it's a challenging but fun process to figure out the shape. Now, once you design the shape and the dimensions and the sizes, you can do a SolidWorks design, like on this right side here. It's optional, but it's also a nice way to approach. Once you have the SolidWorks design, uh, you have your circuit ready, and that's the Dilanka showed us. You convert all the symbols into components so that you can drag them around and do the placements. So you can see here very complex placement, but once you are clear about how your micro mouse looks like, that you followed the sub-step 0, then sub-step 1 is easy. It has to sort of, like based on the online research you did and the ideas you come up with, it has to look like something like this. So you drag all the things here and there and make sure that everything's easily routable. Now this is a very complex step. Many mistakes can happen, but we'll discuss those next week. But for a good PCB designer, always you need to have a rule of thumb. That is, you need to make sure that you are designing your PCB according to some guidelines that you have practiced. Now, Dilanka told you guys to practice these kinds of layer switching guidelines, and then very thick layers for battery. Here you can see battery is very thick routing um, pathway, and these very thin ones for signals. It's a double-sided PCB, that's why it's red and blue. So this is a very crucial step, and most of you guys can come up to this level of designing if you follow a very nice step-by-step path. Now the third sub-step is filling copper in your design, and this is just to show you what it would look like in the top and bottom once you do the copper filling. But we'll discuss more about ideas about how to do proper copper filling next week, because there's a lot of considerations like heat dissipation, how to fill copper around the microcontroller, which is the topic of our workshop series, and then how to do copper filling for other areas which are analog and other areas which are digital. Those kinds of special considerations are there. So this is what the copper filling looks like after you finish that. And fourth sub-step is once you have finalized, check your design using Gerber viewer. This is sort of to get an idea. So JLC PCB and PCB way, we'll be introducing those as well next week. Have this kind of Gerber view. So it's like sort of using all the Gerber files to compile and see what it looks like. So we have given Gerber files of our Medibox project in the Google Drive, and you can try and see what those Gerber files can provide you for the Medibox project. And you can work with Gerber files in the future, and next week we'll show you how to use Gerber files to send PCBs to China for fabrication. And this is what you get from China here, this first circuit. And you can, like, if you become a good PCB design engineer and as well as good at PCB soldering, you can bring this from 1 to 4 like this. You can solder these components, you can solder the microcontroller, you can solder these power circuit components, and then these sensors, the IR LEDs and the photo detectors. So those kinds of components, these are the LEDs for the indication, and the switches and the power supplying units. So all those things you have to step-by-step solder, and there's some kind of neat procedure that you can follow to make sure you get from the start to the finish. These things also we want to introduce next week, how to get fabricated from China, and assemble them once you get back. So this is actually assembled 100% by me. This is back in 2019 August, and it was a very fun experience to learn how to do this as an engineer and as an electronics enthusiast who's very interested in PCB designs. So that was step 5. And step 6, once you're done with the project, you fix the wheels, you fix the motors, and then you get it going like this. So it's a very interesting project, right? You can see that the robot is responding to the distance in front of it. So when I move the book actually here and there, you can see that robot is trying to keep fixed distance from the one. So what you can imagine what's happening, right? This is getting sensor readings inside. So this workshop 1 and 2 combined, getting sensor readings inside, then it's going to get those sensor readings into the microcontroller. Microcontroller is going to run firmware to run a firmware code to determine what the parameters are, and then how to keep the distances, and then it's going to send signals out to the motors, and everything is powered by this batteries, and it's a very nice embedded system. That's the whole idea we are trying to get you guys to get into. So as Sri Lankan students, enthusiasts in this embedded systems area, we have lots of ideas that we can try out. So this article on 70 best microcontroller based projects for students, and many ideas are there, like very nice ideas. Digital alarm clock similar to a Medibox, thermometers, then real-time clock. There was a nice one here. Humidity counter, alcohol detection with vehicle gateway, and GPS and geographical identification systems. So like if you have the imagination, and if you can like get the right steps figured out, all of you can do this, and all this knowledge that we are giving is for you guys to do your own projects. Yeah, so I think that wraps up the presentation. And
some questions also.
okay, let's check the questions in the
And I have to show something like in the very first period, I lost my connection.
yes.
I have to show something like interestingly. This is the motherboard of my old computer. It's also a PCB. I think you can see. And I have another example. This is the one robot that we have built in my university. It has also PCB. I think you can see. And also I have a Raspberry Pi. This is also example for PCB. And this is the one robotics project I have done using PCB. This is another one. And this is the Vero board. It has continuous line connecting. And those are another PCBs. Those are green color. It's a black color. We ordered all of them from China. And I have STM board. This is also PCB. Arduino board. And I have my old Apple phone. I think Apple 4S or something. This one. And this is the RAM in a computer. This is also example for PCB. And here are some my first PCBs. This is the first project I have done in my university. I built a wall following robot. This is the power circuit. You can see LM7805 and capacitors and motor controller, and I have several. And this PCB is in a computer in a DVD-ROM. This is the motor, and it has also PCB. This is also another PCB. And this is my homemade project, also PCB. And I have so many things to show, like so many PCBs, like PCBs everywhere. So this is the basic things, like you like even your computer, even your mobile phone, if you look at your refrigerators, everywhere you can see PCB. So
Yeah.
it's better to learn these basics. So I think you know about breadboards and yeah.
So
And
Dilanka,
yes,
you have like done a lot of projects, right? That's kind of the inspiration all the attendees also need. Since like Dilanka also shared, let me share
I got
this.
some questions. Shall I answer that? Or
Yeah, sure. So the like Dilanka, these are all the projects I have done. This like photo I have. I just wanted to share that from semester, all my 4 years of undergraduate, all the projects. Yeah, so all of you guys have to like get involved in these kinds of projects as well. Yeah, let's go for the questions. I'll share them. You can answer them. Okay, Dilanka, hello.
how
You can take
can
10 minutes and answer.
can I explain how to decide whether to use polarized or non-polarized capacitor? Uh, this is some sort of a electronics related question. Polarized or unpolarized, it depends actually. Um,
So
I think
normally on the schematic designs, they have marked the plus positive sign on the capacitor. If you find the schematic design at positive sign on the capacitor, that means it's a polarized capacitor. Non-polarized capacitors don't have the positive sign, right, Dilanka?
yeah, I showed you example like 22 picofarad capacitor, both leads are equal in length. But when it comes to 0.1 microfarad, one lead is length is higher than the other lead. So high length lead is plus, another short length is minus. That is the difference.
What is the use of using copper core? So
There are,
yeah,
shall I take this?
yeah, can take.
There are three advantages I can tell you. One is they are provide additional heat sinking. Like let's say your PCB like get so much heat like from a voltage regulator or something like that. So it acts as a heat sink. It absorb the heat. It is one advantage. Another advantage is it reduces the amount of H that needs to be done during the PCB fabrication. That means like PCB fabrication process, they have to etching the like you can see if you can remember in my presentation I showed you my PCB like in between copper parts there is a gap like when we are fabricating PCBs they have to etch means eliminating that areas to get copper parts. So if we are making if we are doing copper pour, if we are adding copper pour, the etching part will like reduces. So it it is easy to manufacturing for manufacturer. The etching will reduce. And yeah, those are the things. And yeah, those are the main two things I can remember.
So what is the reason to connect ground in different terminal instead of the same terminal?
Uh, what is the reason to connect ground in different terminals instead? You are asking like in our schematic designing, there are so many grounds, right? Here and there are so many grounds. Let's say you are using only one ground, you have to connect all the grounds to in one place. So it will be mess, right? So that's why we are separating so many grounds, and we put them the same name. We did GND, we named this as a GND. So all the GNDs are connected. So that is the advantage. That's why we are separating them. If we are connecting them, it's become a mess, right? That's what the problem. Is there any piece?
Oh, yeah, PC manufacturer essentially. Sorry, I said that.
I think we can tell those things in our next session because it is more like we are telling you how to manufacture PCBs both in locally and international. What are the ways and how to manufacture? I think we can. Yes, they are in Sri Lanka. They are PCB manufacturers. We will be share those details with you in our future session. This week, try to focus design your PCB, complete your layout, and send us. We will be giving you a feedback. and let's proceed with the manufacturing part. How do we divide these two sectors like shown in the diagram?
I
Which
think
diagram?
he wants schematic sectors to be divided. How to divide schematic sectors?
Shall I share my screen and explain?
Yeah, sure.
I think in a private chat also I got same kind of question, like you are asking how to put a border, ne? This thing. So I remove this. Let's say I remove this, and here in the drawing tools you will find rectangle. Click on rectangle and place a rectangle there, right? And press escape button, and again click on the rectangle, and here in the attributes you will find stroke style. It's on solid 2 you have to change to dash, and it will appear as a dash, and you can place a text also. Okay. Finally it will look as like that. Okay. I got another questions in my private chat. I will answer that. One question is
So I'll quickly take this one. Can we say polarized caps are used for parallel connections and unpolarized for series? No, actually, I don't think that's always the case. Sometimes, depends on the application that we are working on. So we'll try to answer this question in the Facebook group with a proper link to what the correct answer is. So please check the Facebook group for the detailed answer on this one. Is there any China manufacturer? Dilanka, do you have any questions?
yeah, I have one question in my chat. Shall I answer that, or we have to go?
Yeah, you answer that, and we'll finish these ones before 1 p.m.
This one, is there any manufacturer, China manufacturer, to get 3D printed box for our PCBs by sending our solid design? I think you don't want to send these to China. Even in Sri Lanka, there are 3D manufacturers. CB3D also one of the manufacturing company. It's handled by us. So you can place your order from that button, place order button. You can 3D visualize in the websites also. You can place 3D order from here. Yeah, and I have got one question regarding the why there is different layers, like different colors in PCB layout for like red and blue. Red color is I will share my screen again. Red color is, this is a top, you can see here, red color top layer, and blue color bottom layer, and top silk, bottom silk. There are so many layers. You can add layer if you want. Top layer is, we are building a single layer PCB now, so we are focusing on top layer. We are getting top, we are designing our PCB on top layer. So that's what the explanation. Bottom layer is the down layer. We are not using that. And when the 3D designing, if you press this one, it will appear this 3D designing. This is my PCB, and you can change the color: green, white, any color you want, purple, any color. And this is the final outcome. And someone is asking. Explain again this jumper method. I think you will have a recording and you can see that. You have to simply shift the layer and route the path and then paste the wires and then delete the paths and route it again. That's what we follow. Um,
Yeah, yeah.
Questions.
Let's check the last few questions quickly. Right. Yeah, we'll share links on capacitors and regulator circuits in the Facebook group. You can learn there.
Important question, I think.
Yeah. This also we'll share. So this one also, yeah, in circuit fabricating, how they fabricate, we'll share next week. So you can just go for JLC PCB fabrication, and there are videos. We'll share these next week as well, because it's a topic for next week's session. We'll cover that.
I
Yeah,
am important question. Shall I share my screen?
yeah.
Uh,
Which one? This
uh,
one. Okay.
I got it from private, I think. He is asking in the design manager, he is getting process like that. This one, I think exactly he is asking that. This cross means you have errors. Like let's say you run your check design rule check. DRC means design rule check. If we are running that, it will checking your design if your designing design have errors or not. Like this will pop up as you have errors, right? These errors pop up because of my design rules. Let's say go to the design rules. I am setting this kind of things. Like let's say you click on this and you click on this, it will show this one, right? This one, the issue is clearance. And if you click another one, let's say this one, it will show the problem is here. It is also clearance. And all these are clearance problems, right? Clearance problem around this transistor. So what you have to do is transistor is a very small component. Like their leads are very like the gap between leads are very small. So let's say when you are design rule, the clearance is big. That's what the problem. You have to reduce your clearance. Let's say then now we finalize our design. We designed we completed our PCB. So now you can change your design rule to clearance. Let's say 0.1. Now since we have completed 0.1 and control save, saved successfully, and then you can check design rule again. Now those errors are disappeared, right? I think you got the idea. Errors are came because of the design rule you set. You can change, you can play with the design rules and make the proper design. Like first try to design like let's say here there is antenna. Antenna means between two copper paths there is a big copper area. Like it is not a path. This is kind of an antenna kind of thing. So since this is a very small PCB, it won't much affecting. But if you are doing the complex one, it will be affecting to the PCB. But let's say if you want to remove this antenna, what you have to do is go to design rule, set the clearance to let's say 0.8 something, and setting okay, and then reapply the copper bow using the this one copper area. That region I simply mark here and there, and right click, and it will add the copper bow. I think this area may get bigger, but this is not removed, and you can try it with another big value. Design rule check. Let's say this one to set 2. Control save, and then reapply the copper flow. I think you can try this way if you want to remove your copper area. I think the previous applied layers are there, because of that it won't apply. By the way, that's the method. I think I have answered your question. to reduce that error, what you have to do is simply go to the design rule, check your design rules, and you can identify the problem. Obviously, the problem was there. If you are clicking on the error message, it will pop up where the error is. So you can go there and find the error and make a solution using design rule. If you have any problem, ask using our, there is a Facebook group called Circuit Breakers Robotics. So there are robotics enthusiasts all around the Sri Lanka and all around the world are here. So if you are asking any questions, they are already there for giving you answers. And we are also there, so you can ask any question from here.
Yeah, so I share the link. Yeah, let's wrap up the Lanka since it's 1:05 p.m. Thank you everyone for attending the session and staying for almost 4 hours with us. And please join us next week to learn about PCB fabrication, the best practices in PCB design, and further knowledge on microcontrollers, in-depth microcontrollers. And with that, I would like to hand over to Sewandi and her team to close the session.
Yeah, with that, we've reached the end of the second workshop, and thank you for being such a wonderful audience amidst the various technical difficulties we had to face. So we would also like to thank our resource persons, Mr. Kipman Vikramasinghe and Dilanka Vikramasinghe, for delivering such an amazing session. Also, we would like to remind you about our SMS and email partners, Shoutout and YouRead. So our next workshop, as Mr. Kivman mentioned, will be on next week. So join us next week, and our social media links will be put in the chat below. You can stay updated by reaching us out on our social media pages. Thank you.